Over to you, Stephen.
Perfect. We'll just wait a quick moment while I see some of the participants are joining us. Good morning, everyone. Good afternoon. Right, we'll commence now, and I'm sure some more people will join us momentarily. Well, good morning. On behalf of UNITAR, it is my pleasure to welcome you today this session that we are kicking off a webinar series entitled Streams of Change, Exploring the Intersection of Water, Agriculture, and also Biodiversity. My name is Stephen Joyce, and I'm Program Coordinator here at UNITAR that will be hosting the session with some of our colleagues. This session is brought to you by CFL Surrey, also Reclaim, and we'll explore three main panel sessions. First on being able to survey the latest developments in clean water and sanitation for cities and rural areas. Also a panel on opportunities and challenges in providing water sources for sustainable agriculture. And last, a panel on conservation and preservation in considering the roles of what water management play in biodiversity. Throughout this session, we will be offering today a certificate of participation for all those that actively participate in the session, up to 75% of the time that is present. In the spirit of this session, we'll be exploring four main ideas: the water, agricultural biodiversity nexus, the assessing challenges in terms of water access for agricultural resilience, advancing biodiversity and sensitive water management practices, and lastly, being able to translate the integrated water policies in action. Now, today is a very special day because it marks the United Nations International Day for Biological Diversity, which is a very powerful reminder that the health of our water resources is deeply intertwined with the well-being in ecosystems and the sustainability of our food systems. In that regard, biodiversity, it is not only about the rich variety of plants, animals, and microorganisms, but it's also about ecosystems, our lakes, our forests, our wetlands that sustain the life on Earth and provide essential services like clean water, fertile soils, and climate-resilient food systems. This day also marks the commemoration and adoption of the Convention on Biological Diversity in 1992, a landmark agreement which continues to guide our global efforts to conserve biodiversity, use it sustainably, and also share the benefits equitably. Now, before we begin, I'd like to highlight a valuable learning opportunity from UNITAR's Global Water Academy, which we offer a very nice self-paced course on foundations of SDG 6, which I'll provide in the chat momentarily. This features very interactive modules on global best practices that covers each of the 8 targets of SDG 6 and comes with a UN certificate of completion. We encourage you to explore it, and if you have any further questions, you're welcome to contact me, which I'll provide the email in the chat. With that, with no further ado, I would like to hand over the floor to our director from CFL Surrey and co-director of the Institute of Sustainability, and also Associate Vice President in External Engagement at the University of Surrey, our colleague, Professor Amelia Hadfield. Please, Amelia, the floor is yours. Thank you.
Stephen, thank you ever so much. It's an absolute pleasure. This is our inaugural co-sponsored event with UNITAR, and it's really, really fantastic to be on this very historic day to be presenting and showcasing some of the high quality research and the practical case study oriented research that we are specializing in here at the University of Surrey in the Institute for Sustainability, but also from our colleagues in Reclaim, with whom we're just delighted to be able to work. I think the cross-collaboration richness that you get is just unbeatable. This is where we get all the high quality, potent outcomes. So I'm just going to flip through a couple of slides just by way of setting the framework for today and a couple of the ideas that we will see picked up as leitmotifs, if you like, in terms of the panels looking at. So I'm going to just briefly start with the nexus that Stephen mentioned. So that interaction, that cross section, if you like, between water, agriculture, and biodiversity in SDG 6. So we know that water obviously is at the heart of SDG 6. But its reach is colossal, really. It extends across virtually all sustainable development goals. I don't think there's a single SDG where you don't see water as some part, including number 17, the Get Together SDG, including those today, which we're going to be talking about concerning agriculture and biodiversity. So agriculture itself accounts for a whopping 70% of global freshwater withdrawals. And there's presentations later this morning that's going to go into that in a bit of detail in terms of the dependency of that. That's a huge consequence regarding water policies, which directly affect food production, rural livelihoods, and food security. But sustainable and unsustainable agricultural practices, I think, are where we are at now. And we do see these in increasing supply, sadly. We see over-irrigation, we see excessive pesticide use, we see very poor land management, and that has a knock-on effect to water pollution and things like aquifer depletion and loss of biodiversity. It's really interesting that today marks the convention signed in 1992 even, of biological diversity, because that plays a crucial role in regulating the water cycle. We know all about the positive impacts of things like wetlands, helping to purify water, forests stabilizing watersheds, and the sheer, almost impossibly diverse number of species contributing to things like soil fertility. So expect to hear much more this morning about managing water sustainability and equitably. And I think in a sense, we need to recognize mutual dependencies between water, agricultural, and ecosystems. So we're really going to unpick that nexus and try to find out what that looks like in practice as well. We're going to look at urban and rural water management. So what happens when those two butt up against each other? What are those challenges and what are those solutions? Obviously, for urban water management, in cities, there are a number of challenges. Aging infrastructure is one of them. Pollution from industrial water and stormwater runoff, particularly here in Britain. We've seen these profoundly in the last couple of years. Rapid urbanization happening the world over, that's beginning to outpace the water we have, our water service delivery. And that's been leading to inequitable access, particularly, I think, in informal settlements as well. So some solutions are forthcoming, and it'd be great to talk about those. Smart water metering and more green infrastructure like rain gardens and rain roofs. We have a few of these here at the university, but I think we could afford to have more. And obviously wastewater recycling as well. For rural water, obviously, management, we're looking at issues around accessibility, irrigation inefficiencies, and also the seasonal scarcity that the passage of time brings and makes slightly difficult in terms of management. We know many communities around the world depend on rain-fed agriculture. This makes them vulnerable to climate variability. And this means we need solutions. We need solutions focusing on community-based water governance. We have a couple of very exciting case studies to talk about this morning. Affordable irrigation technologies, and of course, protecting what we have, protecting natural water resources as well. And then in terms of the case studies addressing water, agricultural, biodiversity nexus, there are many, many real world examples where those challenges and opportunities intersect. I don't want to give you too much of a preview of upcoming attractions, but we've got some nice local and regional examples. And I think if there's something that I'm beginning to discover here at CFAL Surrey is that the local is the most potent in terms of the research and the potency of that research, because it's based in the community you know. And the community looks to places like the university as an anchor institution, as a source of research intensity as well. But I think there are other case studies out there that I'd like to hear from, particularly when we come to the Q&A. The system of rice intensification that you get in India, for example, farming that actively helps to reduce water use by up to 40%, and that in turn minimizing the need for chemical fertilizers. Kenya. We've seen really great improvement with wetlands restoration in the Lake Naivasha basin, which is fantastic. And that helps, I think, in turn boost livelihoods and ecosystems. And then closer to home in the Netherlands, where there's a really fantastic circular agricultural model looking at water reuse and precision farming, something I confess I don't know a lot about. So we're going to be interested in hearing from our presenters and also from our Q&A, the practical solutions for sustainable water policy and practice. Certainly we'll be looking at those recommendations. They might pop up, if you like, in the following areas: promoting integrated water resource management, IWRM, investing in nature-based solutions, and as I mentioned before, empowering local communities too. And then ultimately, and this is where UNITAR comes in, it's setting that global standard. It's standardizing and regulating and working with local communities to fill that gap, strengthening monitoring and accountability to implement those very much more robust water accounting systems, including environmental flows and biodiversity metrics, etc. So we're really delighted to be supporting this event today. I'm going to talk now very briefly, or introduce, I should say, Professor Prashant Kumar, who is the founder and the director of Reclaim. And he's going to tell you a little bit about what Reclaim is, why it's so important in terms of SDG 6, and then from there, we'll move into the first panel. Prashant, over to you. Thank you.
Yeah, so thank you very much, Amelia and colleagues from the UNITAR for this opportunity. So my name is Prashant Kumar. So again, wearing two hats, so being the co-director for the Institute for Sustainability and also the founding director for the Global Center for Clean Air Research. I guess the most important, the context to this webinar is the Reclaim Network Plus. So as you can see, the banner next to Amelia. So this is one of the networks, multidisciplinary networks, which has been funded by the UK Research and Innovation Council. So there are three councils: Engineering and Physical Research Council, Natural Environment Research Council, and the Arts and Humanities Research Council that has funded this network, which is led by the University of Surrey's Global Center for Clean Air Research in collaboration with the UK Center for Ecology and Hydrology, universities of Bath, Bangor, and Warwick. So the whole idea of this network has been how you can help, adapt the cities against the climate change using the green and blue infrastructure. So what we have been looking as part of the network is various activities in terms of, the developing the case studies that uses the green and blue infrastructure. We have been, running a series of webinars. So we have already done almost around 40 webinars, which have included, around 80 speakers. And each of these webinars are being recorded. We have been supporting the workshops, which has been run by the academics, the the charity organizations, the councils, and so on. And we have also got quite a lot of, the research being produced as part of the case studies. So we funded like 10 of these research projects, which has created those case studies, and fantastic videos are available on the, on the website. So you can visit the Reclaim Network website. You can become a member, and I'm really pleased actually to bring in a number of colleagues today on the agenda, including Thomas, who is also the co-lead, Daniel, who have been contributing to the the project. We have got Balan, who has been involved in the the activities alongside with the other colleagues like Kathy and Devendra. So it's really a pleasure actually to co-host and be part of this fantastic the webinar. I think possibly I'll just stop here.
Prashant, thank you very much indeed. Certainly the interaction, I think, already between CFEL Surrey and UNITAR on the one side, and the profound amount of expertise generated by Reclaim Plus and the Reclaim Network in the past couple of years, it makes for a perfect partnership. I would certainly urge folks to reach out and have a look at the numerous webinars that Reclaim have produced. It's a repository of very real expertise across the whole host of the SDGs. Prashant, maybe you can pop in the link in the chat there. And I think this is a nice takeaway, in addition to the online learning that Stephen mentioned at the beginning, in the form of the UNITAR modules. Certainly, we're excited about being able to support that. I'd also like to thank Dr. Roberta Duchetti, who accompanies me in helping to run CFEL Surrey. It's incredibly important that we recognize and acknowledge the work done by the colleagues. Charlotte, I'd like to thank you as well. Charlotte Leden, who accompanies and works with Prashant in getting Reclaim as one of our key sponsors in a sense and project managers here. So it's time now to move to panel one, surveying the latest developments in clean water. sanitation for cities and rural areas. That's one of the first points that I mentioned briefly in the introduction. So it's my absolute great pleasure to chair this session. We've got about 45 minutes for it. So we'll be looking at presentations from Dr. Devendra Saroj. I know Dev quite well. We had the chance to go to India together not so long ago. And that was a first-class opportunity to be able to see it firsthand. The use of water and sanitation for both cities and rural areas. Dr. Jonathan Chenoweth. Jonathan, it's a real pleasure to work with you. The first thing you asked me to do was to come and help teach on your master's course, which was absolutely fantastic. And Dr. Catherine Pond, who supported me in my hour of need a couple of months ago when I came to you for another UNITAR event, asking for interest and support in things like rural area sanitation and small water supplies. So I'm looking forward to hearing your presentation. So Dev, we'll start with you. And then we'll go exactly in that order. We'll go to Jonathan, and then we'll go to Catherine. And if there's a little bit of time left over, it'd be wonderful to have a bit of Q&A from the audience to make it just that bit more interactive. So that's it from me. Dev, over to you. Thanks very much.
Thank you, Amelia, and colleagues from UNITAR and everybody else. I'll just share my slides very quickly so that I can start discussion on my topic.
Dev, you're on mute, and at this point we can't see your slides. Are you struggling? We can probably share them from this side if that helps.
Yeah, that will be helpful. Somehow I can't share from this side.
Okay, that's not a problem. Give us just 2 ticks, and
Thank you.
We'll have them ready for you here. There we go. Perfect.
Excellent. Thank you very much. So I'll talk very briefly on SDG 6, clean water sanitation, particularly focusing on one very specific aspect, which it stems from some of my experiences in a number of countries across the globe. And the topic is enabling circular economy and sanitation for all. So when I focused on some of the aspects covered in SDG 6, I thought probably it's very useful to present a narrow topic than an whole issue of SDG 6, which is quite broad. So that's why I picked up and potentially learning from this particular aspect, which I'm going to discuss today, is going to be equally helpful to other aspects of the same SDG. So the way many of our colleagues look at SDG 6, particularly from technology intervention point of view, they tend to divide in 2 parts. The clean water part, which is to do with provision of safe and healthy drinking water, and sanitation, which very often is also considered as part of water provision, but very specifically to do with managing human waste, allowing people to have access to safe and dignified sanitation options. So I'm going to be discussing the second bit more closely. So can I go to the next slide, please? So setting up the scene. So we are looking at sanitation, very specifically provisions for toilets and management of the human waste. So we are looking at more than 4 billion people as of today. Basically, they use unsafe sanitation facilities. Of course, you can divide that in different parts. Part of that population having no access to sanitation facilities like toilets, and part of that having sanitation facilities access but not safe enough, not suitable for their needs, and very often not even healthy. And people who are most affected by this could be vulnerable groups. They could include children, and they include other vulnerable groups. So this is very important topic in the context if you try to put together with the health problem and other problems that half of the global population is facing. So basically what we are looking at, the problem of sanitation from a variety of angles. Again, I'll narrow down to very specific aspect of that bigger challenge. So if you split the problem into social, cultural, and financial, in order to bring the sanitation to everybody, sanitation for all, the key question is who pays for sanitation. Of course, there are other issues in terms of the local technical challenges, how to make the toilet suitable for people, make the right design that actually helps people who are actually users of the toilets, take into account cultural acceptability needs, gender issues, and all issues that you can think of in many countries and cultures. But what is common to all is the key question: who pays for sanitation? And models are very diverse. If you go to a number of Southeast Asian countries, the South Asian countries, African countries, Latin American countries, even those locations where the problem is quite immense, the models are quite different. There are people who own sanitation facilities, so have their own toilets, but there are people who have to share it. And there are a number of population groups who would actually access public toilets, and they have to pay for it personally. So it's very complex scenario. And what I have done some work in the Philippines to address some of these situations, the problems in these situations, and come up with potential models that can solve this bigger problem. So next, please. So basically, this is a very interesting picture. The transformation of sanitation systems and technologies and facilities took place in a number of countries in a very interesting way. And I'm giving this example of South Asia and many countries across the globe, developing countries, particularly countries in global South. They took this as a very important learning lesson. And those who are interested in knowing more about it, if you happen to be in India, in New Delhi, there is a museum called Museum of Toilets, and it shows the history of how sanitation um, technologies, facilities, and all issues around sanitation have evolved in a very systematic way. This system was developed during 70s and 80s and really transformed access to sanitation for people, access to safe, dignified sanitation facilities. What is a problem today, even in those places where these type of accesses were provided to people, and especially India has given has been presented as one of the excellent examples in last 10 years, the way they actually transformed access to sanitation. But if you look into bigger uh, the health and environmental issue, the issue is actually what to do with the waste. Okay? In this type of model, it looks like a very sustainable model, because in this case you have a space to actually collect the human waste and let it degrade naturally for a very long period of time, like 2 years of time, and then it becomes natural fertilizer and can be used in agriculture. Fantastic solution for rural part of India. But as urbanization is happening, as space become constraints, and there is little opportunity for having space for building such facilities, there are much more bigger questions arising. What to do with human waste if there is immediate disposal that needs to be carried out? But also it offers a lot many opportunities that I'm just briefly presenting today. Next, please. So the challenge and opportunities both are here. Okay, if you're not interested in a lot of chemistry and the science behind managing human waste, you can ignore the right hand side of this slide. Focus on simple one, the left one. So there are a lot of stuff in human waste. Of course, if you throw into the nature, it causes pollution. But if you try to use science to process it in a systematic way, you can get a lot of things out of it. Okay, so scientists have discovered ways to recover energy, fertilizer, particularly nitrogen, phosphorus, and especially phosphorus, which is an important non-renewable resource. It needs to be mined and then comes to agriculture, as opposed to nitrogen, which is in the air and can be captured in the form of urea and used in the farms. Phosphorus is a quite useful material, and if you get in the right form, basically it can incentivize the sanitation. It has a value which can be converted into some monetary values, and basically it can subsidize this whole sanitation system. Brand good idea. Although a lot of scientists have gone too far to get gold out of human waste, but we are not going that far because maybe of very scientific interest. But when you put the numbers and figures in place, is the nutrients, nitrogen, phosphorus, that makes commercial sense, and especially even in small sanitation facilities, which I have studied pretty much for the first time in Southeast Asia, in Philippines, has shown very promising results. So next, please. So results are very promising for many countries, and could be very promising for a lot many other countries in other regions, is because the special element that is available in human waste, which is phosphorus. Together with nitrogen, it's used as fertilizer, but particularly phosphorus is non-renewable, and it's not available in every country. Also, it's not available in the UK, by the way. Not in Philippines, not in India, not much. So basically, majority of the countries around the world have to deal with this geopolitics, and therefore the recovery of phosphorus from human waste is not only just for subsidizing sanitation, helping sanitation sector to survive on its own, but also it's providing a way to achieve the sustainable recovery of materials, use of it, and recycling in a way that makes whole sanitation, agri, health sector more sustainable in certain part of the world. Next, please. So in short, basically what it can achieve, if you capture the nutrients from human waste, what you can do is to create a closed loop, which means all the nutrients available in human waste can be recycled back to agriculture. We have seen many cases studies in countries like UK. I myself have done some research in other countries like North America, uh, and the general experience is to deal with large infrastructure and large treatment plants. But in most of the countries in global south, this was not seen as potential feasible option because it was seen as a huge technological investment. But it is not true. We can employ the same kind of scientific principles at much smaller level, at the level of toilets, and especially the network of toilets, and combine those as common human waste sources to create fertilizer up to a critical mass value that can create this closed loop system within a small community, where you can demonstrate that human waste can be disposed, processed, and brought back to local agriculture economy. Next, please. So this is the whole idea, the principle that we are looking at. So if we address the problem of safe sanitation, systematic human waste management, processing of it using appropriate technologies, you can pretty much 100% recycle all the nutrients, particularly phosphorus available in it, and create a nutrient supported system, a nutrient economy, you can say, that can help the agriculture, agri-food sector, the wastewater management sector, and it can create a sustainable closed loop system. Next, please. So the scientific base, what is the scientific evidence of it? So this is what we are presenting here today, that it's a summary of the experience from last 8 years in the Philippines, that my team has shown the scientific evidence that actually it is achievable at smaller scales, in smaller settings, and can become part of the local economy. So what you need to do is to invest in establishing a small supply chain, is to invest in a small technological intervention of nutrient recovery system, which is very simply designed, and it's not based on high-tech expensive solutions, but based on locally available technical and know-how and materials to convert basically the septage, the slurry from the toilets, into fertilizer, clean water, and soil conditioner. So next, please. So this scientific evidence has led to this idea. This is available as an open source, as Creative Commons license in University of Surrey's repository, that anybody can adopt freely, can learn from that what is exactly critical scale of application. So it's a scale of application is very small. We are talking about 1 cubic meter, 1,000 liter of human waste being processed to produce a very good quality 5 kilograms of commercial grade fertilizer. It's as good as the fertilizer you buy in the market, the chemical ones, but obviously this is derived from human waste. 20 kilograms of soil conditioner biochar that can enhance the soil quality, and almost 500 liters of clean water. So this is the model that can be applied and can transform sanitation services in many places. Now, I'll very briefly touch the regulatory aspect of it. Next page, please. So what I'm trying to highlight is that a lot of things, even the whole scenario is very different in countries like Philippines and a lot many countries in the global south. Learning from EU regulatory aspects can be really transforming. So what we have experienced is that although scientific evidence does exist, is scientifically well proven, when it go to regulatory bodies, obviously, like in any countries, you cannot just sell any fertilizer or put any fertilizer into soil, particularly if it's for food production. Okay, for non-food production crops, it's easy, but legislations related to food production, they do exist, and they are pretty much common across the globe. So, what many European countries have done during last 20 years, they have basically developed regulation which is scientifically evidenced, and they have created this type of the tables, the guidance and books, which is very helpful. So without going into details of it, what I'm trying to highlight is that if these type of things are scientifically evidenced and created and recognized by regulatory bodies, it can unleash the enormous potential of commercializing fertilizer derived from human waste, because actually it is evident it's suitable and as good as any other fertilizer. Next, please. So the summary is that there is massive opportunities. So besides large challenges, we can focus on these opportunities that that if scientific evidence is digested and put into use, and learning from policies that has been developed recently in countries like Netherlands, Belgium, Germany, France, Denmark, even in the UK, at local levels in many places, what evidence we have is that the regulations like EU 2019/1009, this can be adopted in many countries, and we can explore the opportunities of actually incentivizing the sanitation at much bigger scale. So I will stop here and happy to take any questions.
Jeff, thank you ever so much indeed. Just a huge amount of information there. Thank you for making the chemistry easily digestible, which is helpful. So thank you for that. Gosh, I know there's going to be loads of questions on that, but we wanted to right now to Jonathan, who's going to jump in right after you, and we'll share those slides right now.
Right, good morning, everybody, or afternoon, depending on where in the world you are. I'm Jonathan Chenoweth, a fellow in the Institute for Sustainability at the University of Surrey, and I'm going to be talking on water scarcity, household water requirements, and the impact of desalination. So just as an introduction, SDG 6 suggests that by 2030, we should achieve universal access to drinking water, reduce the number of people suffering from water scarcity, ensure sustainable fresh water supply, and restore water-related ecosystems. So we face a real challenge of how do we achieve these four aims simultaneously when water scarcity is reported to be growing globally? A real challenge that I want to address in this presentation. So in terms of answering this question, I think it's important to keep in mind that globally, water is not scarce. So at a planetary level, we have roughly 1.4 billion cubic kilometers of water. So there's an awful lot of water on the planet. If you look only at renewable fresh water, so the volume of water that could be extracted each year from groundwater bodies and rivers, we have approximately 50,000 cubic kilometers of renewable fresh water available globally, which equates to about 5,000 cubic meters per capita per year. So globally, there's an awful lot of water, and there's even an awful lot of fresh water. So the issue is not the volume of water, it's the fact that water is unevenly spread. So some regions are very well endowed with water, and other regions, such as the Middle East, have very comparatively little water resources. So there's growing concern about water scarcity in some regions. Now, water scarcity is a bit of an ambiguous term. It can refer to physical water shortages, it can also refer to unreliable supply due to inadequate infrastructure, unsatisfied demand, excessive competition for water resources, and depletion of water resources. So all of those things can be referred to as water scarcity. Now, there's been some quite alarming research published in recent years about growing water scarcity. So one of the more alarming reports was published by some Dutch researchers, Hoekstra and McConnell, in 2016, and they reported that more than 4 billion people, roughly half the planet's population, face water scarcity, whereby local net water withdrawals exceed local runoff at least 1 month per year. So they're quite scary figures. But if you look closely at their research methodology, they didn't allow for storage of water in reservoirs. And of course, in areas where there's quite a bit of temporal variation of water over the course of a year, people do build reservoirs. And they also only assumed that 20% of water resources are available for human use. So the rest of the water they assumed needed to be available for environmental use. But of course, in heavily exploited areas, human water use does exceed 20%. And in those areas, water quality in rivers is more determined by having effective regulations and effective wastewater treatment systems rather than in what proportion of water is extracted from the rivers. Obviously, it's better to leave more for the environment if you can, but it's effective wastewater treatment and regulation that makes the biggest difference in water quality in most areas. So there are a number of indicators that are quite widely used to assess water scarcity globally. One of the most common indicators, or most commonly applied indicators, is the renewable water resources per capita indicator. So it's the total water resources in a country, divides that by the total number of people to see how much water is available per capita. So a country with less than 1,000 cubic meters of water per capita is considered to be water scarce, while less than 500 cubic meters of water per capita is considered to be extremely water scarce. So the 1,000 cubic meter figure comes from an estimate of the amount of water needed for food self-sufficiency in an arid environment, while the 500 cubic meter figure comes from assuming that roughly 400 cubic meters is needed for irrigation and another 100 cubic meters for domestic and industrial needs. Another commonly used indicator is the ratio of water withdrawals to supply. So this looks at the total available water resources in the country and then assesses how much of those are being withdrawn. So where a country is withdrawing a significant majority of its water resources, or even more, it's considered to be water scarce, and where it's withdrawing relatively little of its water resources, it's not considered to be water scarce. So a relatively simple indicator. You can see from the map on the slide, it's particularly North Africa and the Middle East that is extremely water scarce under this indicator. The problem with these indicators is they don't really allow for differences in use. So some countries make very extensive use of irrigation, while other countries do not. So there's a lot of variability there. The other factor is that there's almost no statistical relationship between any indicator of national development and either of these two commonly used measures of water scarcity. So you can see on the graph on the slide on the right, I've plotted GDP per capita of countries against their internal renewable water resources per capita. So the first of those two indicators I just talked about. And there really is no statistical relationship between the two. And the same applies if you look at almost any measure of national development. So water for development is very important, but you'll see countries that are highly developed with very little water, but equally countries highly developed with lots of water and huge variability across the income spectrums and level of development in terms of their water availability. So this raises the question, how much water does a person or ultimately a country actually need? So there's a variety of estimates for water needs. Some of the lower estimates suggest it's about 20 litres per person per day, and that's enough to satisfy extremely basic domestic health and hygiene needs. Some of the more generously estimates consider maybe 100 litres per day, which is all domestic health and hygiene needs. So basically all your household needs can be covered in 100 litres a day. Then you've got other estimates that take into economic uses as well. So one researcher estimated it was about 142 litres per person per day is enough to satisfy the non-agricultural requirements in society, plus very limited fresh food production. And then you've got a more generous estimate of nearly 1,400 litres per day, or 500 cubic metres per year, that was estimated as the requirement to run a modern society back a few decades ago. The problem with coming up with any estimate that takes into account economic needs is it really does require value judgments about what sort of quality of life do you expect, what sort of level of economic development do you expect. And there's lots of value judgments about what constitutes a good life. But essentially, humans require water for domestic use, so drinking, food preparation, and personal hygiene. They require water for running a non-agricultural economy, so industrial and commercial water use, and they require water to grow food for agriculture. Now, agricultural production and consumption are increasingly disconnected as almost all countries in the world now trade food in a globalized economy. So there's a huge diversity in terms of countries which export or import foods, and they're not necessarily correlated with their availability of water. But if you look across places that are extremely water scarce, like the Middle East, most of the countries there have adapted to water scarcity by importing bulk grains to satisfy their local food needs. So we definitely need sufficient water at the global level, and the data does suggest that water is sufficient at the global level to satisfy food needs. We have rising per capita calories in terms of food supply, and of course, the amount of water we need globally does depend on dietary choices. So some diets, like meat-rich diets, have very large water footprints. Predominantly plant-based diets have much smaller water footprints. So we do have enough water at a global level to satisfy food needs, but it does depend on dietary choices and, of course, developments in agriculture and making agriculture more efficient. But essentially, food trade is absolutely critical, and very few countries are entirely food self-sufficient. Most countries are heavily connected to the international food networks, and that's how they satisfy their food needs and economic development in some cases. If we look at domestic and industrial water needs, the Food and Agricultural Organization publishes their Aquastat data set, and this basically lists almost all countries in the world, and it suggests that industrial water withdrawals range from as little as 0 in some countries to more than 1,600 litres per capita in places like the US, Canada, or Estonia. Municipal water withdrawals are very variable also, so less than 20 litres per capita in some low-income countries like Somalia or Yemen, to more than 500 litres per day per person in places like Ireland, Qatar, or the United Arab Emirates. So there's very high variability between countries at all income levels. The other complicating issue is that local data doesn't always match FAO data. So in countries that have good local data, such as the Netherlands, the FAO data suggests that they use about 330 litres per person per day for domestic and industrial needs. But the local water authority of Berwyn suggests it's about 120 litres per person per day. So Berwyn publishes some really good breakdowns of water use in the Netherlands, and they suggest that as little as 85 litres per person per day would be required to satisfy domestic water needs in the Netherlands. And that would be assuming that in a really water scarce society, you could recycle showering water directly to flush toilets. But if you're doing that, you could basically sustain a Dutch quality of life with as little as 85 litres per person per day. If you want to look at economic needs, I did some research some years ago that suggested as little as 35 litres per person per day is sufficient to sustain a highly water efficient economy that can provide a high quality of life, high income levels within the country. That's basically a very water efficient service and industrial economy with minimal agriculture, minimal use of water for agriculture. If you allow for distribution losses, and all water supply systems have some distribution losses, then you need probably as little as 135 litres per person per day, or 50 cubic metres per year, to satisfy a person's water needs for sustaining a non-agricultural society that can support a high quality of life for its residents. If you look at the Aquastat data set, there's only 3 countries in the world at present that don't have at least 50 cubic metres of water per person per year available from naturally renewable water sources. There's only 7 that have less than 100 cubic metres of water per capita per year. And all of these countries, with the exception of Yemen, are upper income, upper middle or high income countries, so suggesting they've already got at least a moderate to high level of economic development already. However, of course, total water resources per capita, the indicator from Aquastat, is done at the national level or the country level, so it does hide very big regional differences in some countries, particularly larger countries. But that doesn't, while those countries might be okay at a national level, they could have serious challenges at a local level. Obviously, you can have regional migration within countries, but this can be politically and socially problematic. And equally, reallocating water from farmers, particularly poor farmers, to rapidly growing urban areas is also politically and socially problematic. So there are real challenges there. It's important to think about the impact of desalination. So desalination costs have massively fallen in recent years. Some of the latest contracts in the Middle East for large desalination plants have come in as low as 40 cents, so 40 US cents a cubic meter. So this suggests that to supply 50 cubic meters of water per person per year would cost about $20 per person. So it does suggest that desalination is increasingly affordable, certainly in middle and high income countries in coastal areas. And desalination costs are continuing to fall, which is really, really promising in terms of its future increasing widespread use. Of course, the environmental impacts of desalination are quite significant. So the process is quite energy intensive. And if you're using fossil fuels, then there are obviously going to be considerable greenhouse gas emissions. But hopefully with falling renewable energy costs, increasingly renewable energy can be used. There's also the impacts on the marine environment. You need very carefully designed plants and very carefully managed desalination plants. You're going to avoid significant impacts on the local marine environment. Beyond the impacts on the local marine environment, concerns have been raised about potential to raise salinity more broadly, and particularly semi-enclosed seas like the Red Sea or the Persian Gulf. But I did some research a few years ago that suggests even with massive further growth in the number and size of desalination plants around, say, the Gulf of Aqaba or the Red Sea, the impact of salinity levels in those water bodies would be insignificant compared to the impact of natural evaporation. So there are impacts, but generally the impacts of desalination can be managed if they're managed carefully. So in conclusion then, growing water scarcity perhaps doesn't need to pose an insurmountable barrier to fulfilling SDG 6 and the goal of universal access to drinking water and sustainable fresh water supply. At the global level, we do have sufficient water to sustain growing food production and improve food supply and nutrition. There are relatively few countries that lack sufficient water to meet their non-agricultural water needs if these are prioritized. And of course, desalination can really help in coastal areas where there is water scarcity and it's becoming increasingly affordable. So the real challenges are social, political, and economic, not water scarcity. They present the greatest barriers to achieving universal access. So we need to really prioritize domestic water services and establish effective operation and management of those services if we're going to achieve universal access to drinking water. So that's really a challenge of actually building the services and managing the services effectively. I'm going to leave it there. Thank you.
Jonathan, thank you. Fantastic. Social and economic, political structures being the issue that we need to look at now. Thank you very much indeed. So we're going to turn to our final panelist. It's Catherine, getting her to join. Thank you, Catherine. Thank you. Thank you.
Thank you very much. So we've seen quite a few challenges. I'm going to throw another few challenges at you. More curveballs in this area of water. And a little bit of a shorter presentation, I think, than my colleagues, but I'm going to throw the spotlight on small drinking water supplies, which are quite often overlooked, but are representing or used by some of the most vulnerable populations in the globe. Can you turn this? You don't turn the slides on. Oh, sorry. Do I have a word? Oh, thank you. Yeah, okay. Oh, here we go. Okay. So we've seen already from Jonathan and Devendra, you know, about the SDG 6. Obviously, that's the goal that's central to these topics that we're talking about. And you know, just to reiterate that the goal says that we should be ensuring access to water and sanitation for all. And access to safe water and sanitation is obviously the most basic human need for health and well-being. So it's one of the areas where, you know, getting this right will have the greatest impact on public health. However, it's also an equality issue. We know that women and girls are disproportionately affected by poor water, sanitation and hygiene. And the WHO, whom we work with quite a lot as we're the WHO Collaborating Centre here at the university, have stated that women and girls are responsible for fetching water in 7 out of 10 of households that don't have supplies on premises. So that's, you know, people that are using essentially these small supplies. And we also, you know, I think it's quite well known now or accepted that at the current rate of progress, many of the countries won't meet SDG 6 by 2030. So we need to kind of double our efforts at least, and even that rate of change, we're not going to meet SDG 6 in many areas. So I was told to talk about biodiversity by Amelia. So I've just making that link here, connecting biodiversity and water, particularly in the area of freshwater supplies. So we know that freshwater ecosystems, you know, face a disproportionately high level of threats to biodiversity because of our own actions in terms of agriculture, industry, domestic use, etc., where these supplies are becoming quite polluted. And that also then poses public health threats, and it's very much linked to the issue of small drinking water supplies, and particularly those populations, particularly vulnerable populations that are using surface waters as their drinking water supplies. And there's, you know, been plenty of research that's shown that habitat degradation, reduction of biodiversity may result in an increase in insect and mollusk vectors, which will increase waterborne diseases. So that's, you know, adding to another layer of challenge to these vulnerable populations. So what we're talking about in terms of small drinking water supplies, that often they're decentralised. Why focus on it? Well, you know, we take for granted our water. We go to our tap in the morning. Most of us, you know, we don't think twice about switching on the tap, and there's the water. But about 40% of the global population, and that's both low and high income countries, are served by small drinking water supplies. And these could be, you know, supplies that are serving, you know, one household or several communities. They could be hand pumps, wells, you know, that are protected springs, but they could also be unprotected surface water supplies. And these supplies are often off premise, so they could be, you know, more than half an hour's trek to get your water for the morning. And there's also plenty of research that shows that small supplies are much more vulnerable than centralised systems for a variety of reasons, which I'll talk about in a minute. So just to show you here, I put this slide up. It's from WHO and UNICEF JMP data, and it's showing you the populations, percentage of populations in different parts of the world with access to at least a basic drinking water service. So basic drinking water service, these are the Joint Monitoring Programme definitions, water ladder definitions. I mean, a basic drinking water service is one that comes from an improved source, which has then the potential to deliver safe water, but only the potential. It doesn't say that it is water of good quality, and it's a source that populations can access, or people can access within 30 minutes of reaching that supply. But what's important, so you can see that, you know, in some of the kind of the high income countries, we've, you know, got 100%, 99%, you know, high 90% of populations that have got access to at least a basic drinking water service. And bear in mind, as I just said, you know, that doesn't mean that it's that the quality is good. It's just that that service is there, that water supply is there. But what I've done is I've circled kind of the bottom two regions, Sub-Saharan Africa and the Oceania. And you can see really, you know, only 65%, 60% of those populations have got access to the least to the basic drinking water service. So that means that, you know, 40% of those populations are using a limited and unimproved or surface water supply for drinking. Limited supply means that it's drinking water from an improved source, as I said, which is one that has the potential to deliver safe water, but doesn't guarantee that. But at least you can get to that supply within, it's exceeding, 30 minutes of a round trip, including queuing. But then, you know, you're in these really kind of lower levels where you've got, you know, unimproved supplies. So that's drinking water from an unprotected dead well or unprotected spring. Or also, you know, from surface water. So that's drinking directly from, you know, some of these freshwater supplies, which I just mentioned, you know, which are also under threat. You know, if we don't kind of look after our biodiversity, those supplies are going to become more polluted in the future. And not to mention how they're going to be impacted by climate change. So I've put down kind of a few of the specific challenges that are associated with small drinking water supplies, you know, and they're both social and technical issues. So they're, you know, they're often remote. They're not monitored in many cases. You know, these supplies, people that are managing the supplies have got no financial support. They're not supported necessarily by a utility or government. They don't have technical support. So that's something that's really important. So if your, you know, your pump breaks down or you know, whatever, and you don't have the expertise to fix that, you don't have the financial support to fix that, then it means, you know, that can't be used, and then populations will then have to go and find an alternative source. So they could be going from an improved source to then, you know, really an unimproved source. They're very vulnerable to infrastructure breakdown, which could be due to corrosion of, you know, if they're in various locations where, you know, water's more acid, for example. You know, there's issues now with, you know, the pumps, which are breaking. We're working here with Ask for Water and SCAT Foundation, doing a lot of work on this. And we're doing some work at the University of Surrey on looking at the infrastructure of hand pumps. Another issue is poor installation of the boreholes. So sort of, you know, when the boreholes are some people are putting them without supervision, without the technical knowledge to put those in. So wells can be installed in not in the right places. So, you know, there's not the sufficient yield, or there may be contamination of those supplies. The supply is also very vulnerable to climate change, so increased natural hazards, you know, depleted surface and groundwater supplies, and as I've already mentioned, you know, potentially more contamination of water sources through climate change. They're also very vulnerable to population growth, so you know, there's obviously then the greater demand for water, more people trying to access the supplies, and you know, this is particularly an issue where you've got shallow groundwater sources and surface water sources, and which are particularly vulnerable, you know, where the catchment is being polluted, and pollution may be kind of coming down through the catchment into those supplies. So that's, you know, a real issue where, you know, the supply is surrounded, say, by agricultural lands, you know, livestock farming, etc., and you're getting, you know, very heavy rainfall, which is running the contamination down into the supplies. Functionality, so you know, there's lots of data around on this, and you know, World Bank, even in 2017, we're reporting figures saying 60 to 70% of rural systems are functional at any time. Okay, and that varies obviously with country. But in sub-Saharan Africa, it's estimated that 1 in 4 hand pumps don't work at any time, which is, you know, I think quite a big figure, really. And then you've got 8 out of 10 people without access to water live in rural areas, so they're, you know, already kind of facing these challenges. Lots of issues that are contributing to the functionality. And one of the other areas that we're looking into at the university, with the SCAT Foundation and Ask for Water, is the supply chains of parts of some of the pumps, hand pumps, and trying to put some guidelines together to you know, make sure that the parts that are provided are not substandard, if you like. So, you know, if communities lose access to improved supplies, you know, as I said previously, then they may have to rely on unimproved supplies of a much lower quality, which obviously then has a huge impact on public health. I put up here a few kind of discussion points, I guess, barriers to achieving water sustainability. So there are rising inequalities in terms of access to water sources, natural resource depletions becoming you know, more of an issue, environmental degradation and biodiversity loss. And these are all impacting potentially on small supplies. Climate change is obviously one of those issues, and social development and economic prosperity depends on the sustainable management of freshwater resources and ecosystems. So it's really an issue that we need to get right and to tackle. And in conclusion, I think, you know, we need to improve our understanding of the reasons for and the impacts of failing water supplies. Biodiversity loss and the burden of waterborne and water-related and other infectious diseases affect those populations in countries that are already most ill-equipped to address them, and that's from the WHO. So it's really kind of heaping more challenges on already vulnerable populations. I'm going to stop there.
Catherine, thank you ever so much. That lined up so nicely with a lot of the points that Deb made, actually, too.
Exactly.
And then expanded on exactly by Jonathan, which is fantastic. So we are running right to time. So I think we'll hold questions and go into the next panel. But what I'm going to urge folks to do, and perhaps Stephen can keep an eye on this, is putting questions in the chat, and we'll be able to pick those up hopefully going forward. So we're going to move on right now to the second panel, opportunities and challenges in providing water sources for sustainable agriculture. So shifting out of cities and rural cities into sustainable agriculture. And this is going to be chaired by Prashant Kumar. And we've got 2 splendid panelists, Dr. Daniel Green, who is a reclaimed fellow from Harriet Watson, joining us from Japan, which is fantastic. And here in our studio, Dr. Belen Marzi Cardona, who's an Institute for Sustainability Fellow. So Prashant, we'll switch over to you for this one. Thank you.
Yeah, so thank you very much. It's been going on amazingly well, and I have a pleasure of chairing this particular session. And as Amelia said, we got 2 fantastic speakers. We got around 45 minutes, which is going bang on time, which is really happy. We will have the both speakers to speak for around 15 minutes or so. And then we'll take the questions in the end, right? That's what we are doing, right?
I think we can do that.
Yeah, so I believe that there are 2 ways of asking questions. So you could possibly use your chat box and write your question with your name and affiliation, so I can speak with it. Or maybe you could use the Q&A box actually, which is more sort of appropriate. So you just write it up, and then I will pick it up actually for you towards the end and ask our speakers. So without any further ado, so I have a pleasure of introducing Daniel Green from Harriet Watson University to talk about his work actually, who he has been doing as part of his research. And it's been a pleasure to have Daniel as part of the Reclaim, where he has contributed to many activities, including webinars, projects, and you know, there's been workshops and so on. So he's been a fantastic, you know, the researcher working in this domain. Yeah, so I guess without any further ado, I can possibly ask Daniel to share his screen and start his presentation.
Brilliant. I'll share now. So hopefully that shares and you can see my screen. Just make it full screen now.
I can see the screen, yeah. I think
Yeah,
you can
great.
make it full screen. Perfect.
Yes, brilliant. Okay. Thank you, Prashant, for the very kind introduction. I got involved in Reclaim through a helping with run a green infrastructure workshop about a year and a half ago now, and also was lucky enough to do a Reclaim short-term knowledge exchange visit with the Royal Botanic Garden, Edinburgh. So I'm an assistant professor in nature-based solutions based at Heriot-Watt University within Edinburgh. As part of the Reclaim network funding, this actually allowed me to become a research associate and sort of formalise my role within the Royal Botanic Garden, Edinburgh. And then today I'm going to be talking about some work which is predominantly done at the National Green Infrastructure Facility within Newcastle. And the talk that I'll be giving is on environmental monitoring and experimental data collection of nature-based solutions. So I just wanted to put this kind of 4 pillars of SUDS to give you an overview, those that aren't familiar with sort of nature-based solutions, green infrastructure and sustainable drainage systems, or SUDS. My research focuses mainly on the sort of flood risk benefits of SUDS, so actually managing sort of rainfall runoff of kind of within cities. But SUDS actually have a really sort of holistic and multifaceted benefits. So this shows some of the additional benefits. We can see water quality. We've got the biodiversity within the cities.
Daniel, sorry,
yeah,
the slides are not rolling. Can you try?
They're not updating.
No. Can you put it on?
Okay. Let me just try and share again. Let's see if maybe if I go on this and then go back onto Zoom. Is that better now? Can you see the sort of the 4
Yes.
pillar?
Yeah,
okay. Great. Okay, yeah. So my research is kind of on the water quantity, the flood risk management side of things within cities. But SUDS also have these 4 pillars of SUDS design, and we can see here the water quality, so the sort of pollutant removal, biodiversity, and also public amenity and creating beautiful spaces within cities. I just found this paper just before we started the session, actually linking green infrastructure and how it feeds into the sustainable development goals. And this paper sort of highlighted that 17 of the goals are targeted or included by nature-based solutions and urban green infrastructure. And actually 74 of the targets are kind of contributed towards through green infrastructure. So obviously, one of the primary focuses would be sort of the climate mitigation. We can use like low emission materials to try and reduce carbon footprint when we're developing these. My research maybe focuses more on the disaster resilience enhancement and kind of risk reduction, but also the health and equity and minimizing pollution and also ensuring the access to clean water as well. So I think it's quite nice to work in an area where green infrastructure can feed into providing sort of holistic solutions to a wide range of problems that we're facing in today. And also, whilst I'm on this point, the sort of focus of this this session is obviously agriculture. My research is more on urban sort of green infrastructure, but it's interesting. Like I work quite closely with colleagues in Brazil, and they're very focused on green infrastructure for sort of agricultural water reuse and how these systems can be almost transformed or transferred to tackling those kind of issues. I'm currently in Japan as well at the moment, so here for a 2-month research visit in Kyoto, working with the University of Kyoto. And within Japan, there's primary focus of green infrastructure is actually on the sort of public amenity and the beautification of urban spaces. And in the UK, we're kind of maybe more focused on green infrastructure for flood risk management. So hopefully this slide changes now. Yeah, so the background and scope of my talk, I want to talk about green infrastructure. And I think really the next step is to adopt green infrastructure, SUDs and rain gardens within cities to try and ensure that we're creating sort of resilient areas and resilient urban areas to achieve net zero targets. One of the key problems that we face in the UK and also globally, actually, is that monitored data to try and provide the evidence base of to assess and maximise the performance is currently lacking. So actually, we sort of recognise that green spaces within cities and bringing nature into cities is a good thing, but actually, we want to know how good it is. So the purpose of my talk today, I'm going to be talking about sort of high resolution monitored data from some fully functional pilot systems that we set up at the National Green Infrastructure Facility to try and provide some input parameters to aid hydrological modelling and to assess the performance and functionality of green infrastructure. So this is what we were working with within this project. So this is some work that was conducted as an EPSRC research grant between Newcastle University and the University of Sheffield, commissioning and setting up these bioretention cell rain garden lysimeters. So we can see from this rolling video, I'll just carry on talking as this video plays. We set up 4 large-scale lysimeters, which are 2 meters by 2 meters in sort of surface area with a 1.2 meter depth. And these were split into 2 hydrologically isolated cells. Now, as I've said before, the sort of key focus is to commission these to provide pilot scale analyses of bioretention cells or rain gardens operating under both natural and simulated weather conditions. And these systems were identical in design specifications, apart from featuring different vegetation planting styles, which we can see in the bottom right-hand corner of the slide. So we had a sort of reference, no evapotranspiration scenario, bare earth. The next step up was an amenity grass, which is quite standardized in kind of swales and other urban features. And we also had 2 sort of larger crops, so the Iris sibirica and the Deschampsia cespitosa. Now, these represented 2 larger species with greater biomass and a higher evapotranspiration scenario to compare the influence of plants within these systems to try and remove water from the soil. And this just shows a very basic kind of cross-section of the engineered SUD soil profile. This is based on sort of international design specifications, and this allows kind of the plants to grow, but also water to move and be stored within the soil profile. Now, this also went out below the systems into the combined sewer system and was infiltrated into gauged outflows, so we could measure that. And this next plot just shows a sort of distributed in situ network of all of the sensors that we had measuring inflows, soil storages, and outflows. Actually, I haven't put a link to this, but we do have an online data app where all of the lysimeter data is automatically uploaded and available online. So if you search for the NGIF data app online, you should be able to find that. And this just shows that soil and the sensor network in a little bit more detail. So we can see here some of the key sort of sensors we use to obtain some of these variables. One side shows the key processes, so precipitation entering the system, infiltration, percolation as water moves through the system, and also losses in terms of outflows and evapotranspiration. And the sensors were put in situ to kind of understand how water moves through these systems. So inflows, storages, and outflows is the key kind of components of the system here to understand green infrastructure, mass balance, and performance. I'm going to skip over this. This just shows the difference between 2 of the sides because we use these we had two sides, an unrestricted and a restricted. So within one of the cells, the outflow was completely unrestricted, allowing water to pass through freely, relying on the soil to do all of the retention. Whereas one of them had a restricted outflow to try and hold back water and almost assist the soil in its functionality. So yeah, this gives a sort of brief overview of some of the data set. We can see within each of the lysimeters, we had about 130 separate hydrological, climatic, and soil-specific variables measured at about 5 meter time step per lysimeter. Just quite simply, the data illustrates the links between the soil and the climate parameters in relation to inflow storages and outflows. Highlighted here areas of sort of drying and wetting associated with decreases or increases in the precipitation, and the outflow sort of represented that. We can see as well as we kind of go deeper into the soil, we see the retention rate, then the moisture retention is less fluctuating, less pronounced fluctuations with an increase in soil depth. And the soil water moisture content sensors are very, very fluctuating near the surface, sort of representing the proximity to the surface of the soil. I want to move on. So that was some of the sort of longer term data. I want to move on to some sort of in-field testing and how we can look at performance of these systems. And I actually had a meeting with Kyoto City Council today, which was a really interesting kind of comparison between the UK kind of SUDS. We're very, very focused on the hydraulic conductivity and the ability of water to move through the soil, whereas Japan, coming from a more sort of focused on plants within cities and actually making the public space more green and inviting to people, they're not really focused on this saturated hydraulic conductivity. It's more about allowing plants to thrive in urban environments. But yeah, so in the UK context, bioretention cells are a sort of functional role of reducing urban flood risk, and the soil and the vegetation components are really key at actually providing that capacity for retaining stormwater and also determining outflow discharge and also runoff rates into nearby grey infrastructure systems. Now, we use this kind of metric, saturated hydraulic conductivity, to almost assess and determine design performance of SUDS performance. And in the UK, a guidance of 100 to 300 millimeters is sort of set as a good standard for allowing these systems to retain enough water to actually have a functional flood risk purpose, but also without becoming waterlogged. So it's quite a fine balance between retaining enough water, but not retaining too much water that these systems actually kill themselves. One of the kind of key problems, though, is that actually in-field evaluations of these systems is very, very rarely conducted, and you would expect that this would vary with soil depth and across different vegetation types as well. So within these lysimeters that I've explained before, we did some initial kind of characterization of the soil, and this the pre-filling soil gave a KSAT value of 101 millimeters per hour. So at the lower end of the Syria SUDS manual guidance for infiltration rates. However, when we conducted some in-field surface measurements using this Saturo dual head infiltrometer, we saw considerably higher readings, potentially because of the plants, but also potentially because of settlement. So this led us to think, well, actually something strange is going on here. And so we use this equipment here. You can see a Guelph permeameter, and we augured a series of boreholes to understand changes through the soil profile. So yeah, this Guelph constant head permeameter was used to determine how KSAT changed with depth across different vegetation types. This plot here, we can see that we've got different testing depths through the SUDS soil profile, and we repeated these 3 times as well to understand differences associated with soil heterogeneity. And as well as this, particle size distribution tests were conducted at each of the sampling or the testing depths to understand particle size distribution and field moisture content changes. So some of the results, we're currently in the process of putting this into a model so we can replicate what we saw in the lysimeters using a 1D model. But we can see that all lysimeters have higher KSAT at the near surface, which is thought to be because of weathering and wash-through processes, which we'd kind of expect being close to the surface and close to any rainfall inputting into the system. Now, KSAT generally decreases with a soil depth, and this is possibly due to consolidation and compaction under the weight of the soil itself until we get close to the drainage layer, which again is what we'd expect because the drainage layer is put in to allow free drainage out of the system. And I actually haven't included this on the figure here, but these kind of peaks here, so we see the Deschampsia cespitosa peaks around 500 millimeters depth. This is thought to be because of the vegetation and the rooting depths, allowing sort of preferential flow pathways. So this is actually the sort of point at which the roots ended. And I think this kind of plot really quite nicely shows that actually the use of a single KSAT value, which is kind of what we're using in the UK at the moment, may not actually be suitable for characterizing the hydrological performance and the ability of these systems to allow water to freely move through. So we actually need to use potentially different metrics. I'll just quickly skip over this very quickly because we can see the difference between different vegetation planting types, which might be quite relevant for agricultural perspectives as well. So the modelling that we're doing is actually based on agricultural work, and we're sort of applying agricultural research to urban systems. But we can see the field moisture content shows variations with the different planting styles that we examined. And this is sort of associated with plant biomass. So the Deschampsia cespitosa is a very, very large plant biomass, and that has much lower field moisture content in comparison to the bare earth and the amenity grass, for example. So yeah, bare earth, high field moisture content. And this reflects actually the water able to get into the soil as well, because we've got no canopy inception or plant transpiration losses from the system. So yeah, moisture content within these systems generally correlates quite nicely with plant biomass and the increased transpiration with larger leaf area index. And when we look at the soil textural changes, this plot here just shows the root mean square error. So comparing it back to the reference sample that we initially filled these systems with. Yeah.
So can we close it in a few minutes?
Yeah. Give me one minute.
Yeah, no problem. Yeah, thanks.
Yeah. So yeah, we see that the bare earth lysimeter has a higher gravel content at the surface, and we kind of suggest that this is due to wash-through processes associated with that increased weather exposure. And interestingly, this is something that we're currently exploring more in depth. The Deschampsia cespitosa, so the tufted hairgrass, actually kind of amended the soil because of its root action and the biological weathering of the soil. And this has implications for how green infrastructure in cities changes and the maintenance requirements through time. So I'm going to skip over this work here. This was some work that we did at the Botanics. And I will end my presentation here, but happy to take any questions after or within the Q&A session. So thank you.
Perfect. Yeah, thank you very much. Yeah, sorry for cutting you off. I think we are in the interest of time. We wanted to give opportunity to our second speaker in the session, which is Dr. Belen Marti Cardona. So Belen is one of our colleagues at the University of Surrey. She's been doing fantastic work in the area of water and the flooding and the nature-based solutions in a lot of these areas. So Belen, yeah, over to you.
Everyone, thank you for your introduction, Prashant. As he said, my name is Belen. I work in the intersection between Earth observation and hydrological modeling for integrated water resources management. And that has a very important part on sustainable agriculture. And if you don't mind, do you mind if I pass the slides myself so I can use the
clicker is slideshow.
Will I be able to point at the slides with this?
Yes, but the people online won't be able to see.
Okay, so if
You
you,
can do it here if you want.
if there is no problem with that, I will use it so I can point.
Yes.
I need to interact with the slides. Not when I Well, I have to say I maybe prepared. Can you hear me well online from here? Yes, is the microphone?
Yeah.
Yes.
Sounds good.
Yeah, sounds good.
Perfect. So I think I prepared my slides a bit with a different structure than some of my colleagues here. I thought of a panel and giving opportunities for discussion. So I prepared a few slides with key points, touching on key critical points to provoke questions and trigger discussion. Talking about sustainable agriculture, water for sustainable agriculture, I would start saying that fresh water is the backbone, is at the foundations, is underpinning any food production on land. And what are the problems of insufficient water? Water stress on crops, soil degradation, soil organic carbon is a very important quality of our soils. Particularly on farmland, lack of water scarcity induces also increased salinity, erosion, and all this water stress, soil degradation yields to or takes us to lower yields, lower food production. And also water stress causes reduced livestock carrying capacity. So again, lower food production per cubic meter of water. And we all probably have on our minds this broad figure that obviously is very geographically changing, but we can say as a rough number that 70% of the anthropogenic abstractions of water go into farming. No, yes. So the title of our talk was about challenges and opportunities, if I remember properly. So I prepared a slide with key challenges to discuss about. And the most important ones I came up with in terms of sustainable agriculture and water in the context of water resources are population growth. That's one of the main challenges we have. Population growth means higher food production to feed population and higher consumptive use. And I would like to stress this consumptive because when we think of increased needs of water for population, we think of domestic water, water for sanitation, but actually those uses of water are not consumptive. So they don't really reduce water availability in terms of amount, because the water we abstract from a river to supply to our cities is treated and returned to the environment in very much the same amount. We may introduce pollution, obviously, but in terms of water, it's not really a worry. What really deprives us or reduces our water access is the food production, is the evapotranspiration from plants, because that takes water from our catchment. When we talk about water availability in terms of hydrology, we always think of catchments, not countries or regions. It's really catchments, which is like a special unit where we share water resources. And the really loss of water from a catchment is the evapotranspiration, evaporation and the transpiration from plants. So feeding a higher population means in terms of water amount, way loss, higher use of water. Then we have climate change. And it's not only that we have to feed a higher population, it's also that the climate warming means that for producing the same amount of food, we need more water because the evapotranspiration, the potential evapotranspiration increases. And actually, if we compare this potential evapotranspiration to the precipitation, that is the key factor that we are worried about in terms of food production. This ratio is what gives us an idea of the aridity of our region. And 3/4 of the world, this was published in a very renowned journal very recently, 3/4 of the world are getting more arid due to climate change. More arid and less water means lower yields. Another problem, another challenge, we are talking about challenges here, is the unreliability of water availability or the increase of extreme events. That also poses a risk in terms to ensure crop production. Despite these challenges, 1/3 of the world is getting more water. And there are also other areas that may be benefiting from climate change in terms of food production. Climate warming is making that some soils that used to have a permafrost, used to be frozen all year round, they are melting and they are becoming arable. So some people in Siberia, for example, are very happy because they are gaining farmland. But as I said, one that is in a small part of the world. It doesn't compensate those who are losing productivity in their soils. Other key challenge for agriculture in terms of water is the pollution and emissions. Rice is such a key staple food for a huge percentage of the population, the main staple food in Asia, for example, and it causes tremendous methane emissions. The power of rice farming in terms of greenhouse gas emissions is almost equivalent to the greenhouse gas emissions from the entire aviation industry. We've been working quite a lot on how to reduce those emissions with the proper water management in rice crops. We have the problem of aquifer depletion. What happens in arid regions where the precipitation is reduced, the evapotranspiration is increased, people resort to the groundwater aquifer with the storages, but they are abstracting at a higher rate, at a rate higher than the recharge. That is causing an aquifer depletion. That is obvious. There are tools, remote sensing tools to monitor that. It reduces the gravity. It reduces the gravity when we reduce the content of water in the soil. We've seen that very clearly, for example, in different areas. In Afghanistan, it's very obvious how you see with satellite images, suddenly you get a solar panel, then a pond next to it, because we are using the power from the solar panel to abstract water from the aquifer, put it in a pond, and then irrigate. And a very arid area becomes very green. And that increases, and you can measure that, and you can measure the losses in water due to these new crops, which are depleting the aquifer. Obviously, this is provided good now, but it's depriving of these resources for future generations, not sustainable. And 2 points that I would like to stress here, because it's where we have quite a lot of power to act, is equitable water access and transboundary catchments. And I will illustrate that with a little bit of work we've done here. I realized I didn't put references. I mean, there is some published work for these topics. The thing with equitable access is that, as I said, we share the water resources within a catchment. And whatever we do in a catchment has an impact on downstream users. And so I may want to abstract water here to get healthy crops of maize, but that is going to reduce availability of water to users downstream dramatically. And that's where using these integrated water management tools, we can say, look, you can abstract up to this point or not being in detriment of your neighbor downstream. This raises quite a lot of conflicts, particularly when we have transboundary catchments. They become even more conflict. That's where water is even weaponized. And look now at India and Pakistan. Look at Iran and Afghanistan, Bolivia and Peru. There are many examples of those transboundary catchment conflicts. And I thought it was a good moment of bringing up some of these challenges that have been brought to us by stakeholders, real stakeholders who came up and said, look, we have these problems of groundwater over-extraction in Jordan, and we need help from you. We are meeting with them in a few days as part of an initiative of the Office for Outer Space Affairs. We are going to help them to use satellite data with numerical models to address these issues. This is another example. There are quite a lot of them. There are quite a lot of stakeholders that have stepped up with these problems. Another one is here, integrated water resources in Pakistan. They were saying, well, we are growing rice or we are exporting rice, but every kilogram of rice production takes up 3,000 liters, even more, of water. That is not sustainable in the future. We cannot rely on this export of rice because we won't have enough water. And I think it's wonderful that someone stepped up and identified this problem. Because normally we look in terms of economic growth and benefit in the short term. And we look at selling rice, not that we have enough water. So hopefully we will be working with them in a few days. And I thought that we could showcase, as my colleagues have done, some of the research we've done here. This is one of those examples that illustrates this unfair use of water within a catchment. This is an area, this was within a project with funds from the United Nations Development Program. Not that I messed up the acronym here, is in the Spanish order. This was done from the University of Surrey with a memorandum of understanding with two Bolivian universities. And what we've done here is drawing the catchment of a lake here called Popo. It's in the country of Bolivia in South America, and all this catchment is in a high elevation plateau in the Andean mountain range. It's a catchment. It doesn't drain water outside of the catchment. And what happens with this lake is that it receives most of its water from Lake Titicaca through a river here. And it's
Belen,
yeah.
Can I please ask to wrap it in 5 minutes?
5 minutes?
Yep.
Oh, that's a lot of time. I have one or more.
Okay, I was being generous.
Thank you for the warning. Here we have this river that provides most of the water to this lake, Popo. And what happened here is that there was, on this graph, we see the water level in Lake Popo in blue, how it was being reduced quite strongly for some time. And that coincided with a period of boom in quinoa crops. It became one of those superfoods. I didn't know what it was when I was a child, and now is such a healthy food. So this is the main production area of quinoa, or one of the main in the world. And many farmers around this river started growing quinoa, and that caused abstractions of water from the river, and this lake lost water. Here, there are some dramatic images of lake. But what happens that there were here around Lake Popo very old communities of people who were living on this lake, on fishing, on cattle, and some of them had to emigrate. So some sort of regulation of capacity to say, well, limit the capacity for abstraction to maintain, to sustain this lake. Well, that's something that is in our hands We have the tools, we have the models, we have the satellite data. That's something where we can. And I think, yes, well, this is just an example of the things we can do. We use over 60,000 satellite products to map the areas that were really increasing the loss of water. We can see here around the river, in color map, the trends of water loss. In red, we are saying the increase of water loss. And we also mapped and quantified them by land use. We saw that the water loss was being increased, was being split up in agriculture areas. So that was about challenges, and a very quick one about opportunities. I think I already referred to it very quickly. Opportunities, we can offer integrated water resources management tools that can look at the catchment scale to the justice in water allocation. We can train on these tools, on Earth observation, integrated modeling. And actually, just this week, we submitted a little proposal about exactly that, about advancing integrated water resources management together with Earth observation that is not exploited enough, and together with projections of climate change. So this allows to answer questions like, what if I increase my farming area in this part of the river? What will be the consequences for my downstream neighbors, and how these consequences will evolve with climate change? That's it. Am I on time, Prashant?
You've done fantastic job. Yeah, thank you very much. It's just the bad sharing from my side, running over time a little bit. But I think we got next session, possibly we'll recover that time to come back to, come back on track. So first of all, thank you and Daniel for the fantastic presentations. Does any of the call has any questions for our speakers? Maybe we could just accommodate one question each, if there is any. No? Okay, maybe then I can ask actually one question, and possibly both of you can just reflect in a very short kind of way. I think this is a fascinating work you have been doing, but if you wanted to tell to the participants, what would be one kind of take-home message from your talk in a very simple and a short sense? That would be really helpful. So maybe Daniel and then Belen.
Yeah, okay. I guess my take-home message would be, I think green infrastructure, we need to sort of try and integrate it into cities as much as possible. I'm possibly going to be a little bit biased, but I think, yeah, like it has huge potential from a number of different standpoints, like climate risk reduction, as global temperatures get warmer as well, like the sort of heat wave and passive cooling benefits, flood risk benefits as well, pollution control. So I think green infrastructure has the potential to solve a lot of the sort of current and future challenges that we face. But I think we need a bit more evidence on its functionality. That would be my sort of overarching take-home message.
Thank you. Belen, what do you think?
Well, my take-home message would be, it will be obviously biased as well, because is the integrated approach. Water is too much present in everywhere. And sometimes trying to fix one thing, we may cause problems with the other. So, and I think we're using modeling tools. We can.
Mm-hmm. Okay, perfect. Okay, so I think in the interest of time, we will move on to the next session, which is Reclaim Case Studies and Actionable Solutions. So I've got one of our co-leads from the Reclaim Network Plus, Dr. Thomas.
Actually, we're going on to the next panel is conservation and preservation.
Oh, sorry, I almost missed actually that.
We'll
sorry.
get there, don't worry.
Going back to you, no problem.
That's all right, don't worry. So we're going to be looking at water management in biodiversity. So here we have another two-step presentation. Right now we're going to turn over to Louise Firth, who joins us from University College Cork. Absolutely one of my favorite places in Ireland to visit. Lots of wonderful colleagues there. And then we have the pleasure of coming back to Belen. She's really putting the time in this morning, and we're really delighted to do that. But at this point, Louise, over to you. Thank you for joining us.
Thank you, Amelia. Am I sharing the right screen?
You are. Yes. Thank you.
Brilliant. Yeah, thanks for everyone, and thanks for the opportunity to be here. My name is Louise Firth. I'm a marine ecologist at University College Cork in Ireland, and today I'm going to talk to you about a specific project that wasn't necessarily funded by Reclaim, but it's relevant to Reclaim, and I'll bring in the workshop that we had funded by Reclaim a little bit later on after this case study. So I've entitled it Accidental Nature-Based Solution, Mussels, Water and Urban Biodiversity in the Liverpool Docks. Okay, so I'm sure we're all very much aware that we as humans, of course, are transforming the global coastline. In estuarine environments, we are filling up our rivers by reclaiming hundreds of thousands of hectares of land and building cities in them. And the top picture shows you a very urbanized environment along a river. And of course, in more open coast environments, we are building artificial islands. The image that you can see in the bottom right is, of course, the very famous Palms Island in the United Arab Emirates. We published a paper last year where we coined the term the palm effect, with the view that since the construction of the palms in 2001, there's been a sort of a global precedent where lots of nations are now building these iconic islands in the shape of all sorts of weird and wonderful national identities. But yeah, we just refer to it as the palm effect, which we do believe is a thing. And of course, with all of this urbanization and artificial island building, there are of course many different types of artificial structures that we place in the marine environment, and they can range from seawalls, groins, wharves, docks and piers, pontoons, floating structures. All of these structures, of course, anything you place in the marine environment represents potential habitat for marine life. If you threw a shopping trolley or a cone in the marine environment, it will become colonized. So whether you like it or not, everything is habitat for something, and that's true on land as well. That's not me advocating dumping in the marine environment, quite the opposite. But this image here is showing you the sort of underside of a floating dock, a pontoon. And quite often these artificial structures are colonized by either invasive species that are not necessarily welcome to that environment, or more commonly, they're actually characterized by organisms, lower diversity than analogous natural environments. So typically when we're talking about marine artificial structures like groins and breakwaters and seawalls, the analogous natural habitat would be rocky shores. Occasionally, we do, of course, get organisms colonizing these structures that may be important for a range of reasons, ranging from ecological, commercial, or sometimes conservation importance. I'm going to talk to you about a case study in the UK. So this is the city of Liverpool. I'm just going to look at the screen over here. And this is a map here showing you the Liverpool docks, which is basically all stretched along the eastern shoreline of the River Mersey. And you have the city of Liverpool over here on the right-hand side. The name Liverpool, of course, some of you will probably be aware of this, comes from this structure here referred to as the Pool. This was originally a creek, which was later infilled by land reclamation to build the modern city of Liverpool. And you can see here that this is just showing you some of the docks along the east shoreline of the Mersey, stretching from the south docks to the north docks, but they do actually extend 11 kilometers all the way to the north there. So Liverpool really is characterized by a very long history of reclamation, and I don't necessarily mean reclaim in a positive sense that like reclaim means it. I would say more like claiming the land rather than a reclamation. There's about 300 years of history of land use change in the Liverpool area. Up until World War II, Liverpool docks were a highly active and important environment from a trading perspective. But after World War II, when it came to containerization, the docks went into disuse because larger ships and that were carrying containers could not make it into the small docks that were built in the 16th century. So over time, up until the 1980s, the docks went into disrepair. In the 1980s, the city of Liverpool got funding to restore the docks, which they were then restored in 1984. Steve Hawkins, I don't know if some of you are aware of who Steve Hawkins is, but he's who was a professor at the University of Liverpool and the University of Manchester. And he and his team conducted a lot of environmental research following the restoration in the 1980s, all the way through to the end of the 1990s. So there's a huge number of studies, papers, theses that were produced during this time looking at the docks and how they responded from a biological and also an environmental perspective following the restoration. We received funding from NERC in 2012 to go back and revisit the docks to look at the biodiversity colonising the quay walls. And then we also revisited in 2022, which gave us a pretty unique 40-year perspective post-restoration in this environment. One thing that's important to note, over this time period, there was a change to the hydrological regime of the docks. Docks were primarily marine, okay, almost fully marine freshwater, mostly influenced from the tidal River Mersey. But in 2009, the Leeds-Liverpool Canal up here to the north of the image was actually connected to the Liverpool docks here via the Liverpool Canal link. And that, of course, changed everything because it now brought fresh water right up into the dock system here. And all of the docks are interconnected. They have lock gates, of course, but it does mean that there's potential for the influence of the fresh water. So focusing on Albert Dock, I'm sure many of you have visited the beautiful Albert Dock, which was up until very recently a UNESCO World Heritage Site. The image on the left here is showing you a photograph of the docks in 1980 prior to the restoration. And you can see that there's no water currently in the dock at that time. The lock gates had been closed and there was no way for the water from the Mersey to actually get in. And you can see it had completely silted up. Many of the buildings were left derelict and it really was, in a very sad state of repair there. But in 2015, this image on the right is showing you what it looks like pretty much today. It was a UNESCO World Heritage Site up until 2021. And you can see here, of course, the water was replenished, the buildings were restored, and of course, it's now a thriving, healthy environment with lots of tourism and trade and all sorts of things going on there. A wonderful city to visit, and the UNESCO, the Albert Dock is very much a centre of that. Obviously, in an environment like this, where you have all of this activity and importance, good water quality is, of course, essential. So I told you that Steve Hawkins and his team did a lot of work in the 80s and 90s. This image is just showing you the early biological colonization up until about 9 years post restoration. And this image is taken from a paper by Steve and many people from 2020, including myself, and which provides a very comprehensive overview of the many studies and the whole story relating to the wider River Mersey, if you're interested. But just to sort of point out, there we have the first arrow showing you the restoration in 1984. So this is where the lock gates were restored, the water was returned, and they basically started to see the recovery of the environment. And this is just showing the biological colonization. And as you can see, the first organisms to come in were barnacles and bryozoans. So these are invertebrates that are filter feeders, which is significant here. This second arrow, about 5 years after the restoration, shows you in 1989, there was a natural settlement of mussels, and this was very significant. Prior to the mussels settling, there had been a number of trials, unsuccessful trials, actually transplanting mussels into the docks to see if they would survive. And the idea behind that is because mussels are filter feeders themselves, and that the hope was that the mussels might play a role in improving the water quality. Very fortuitous natural colonization, which led to all of the docks becoming completely colonized by a massive cohort of mussels back in 1989. And I can tell you that if you follow this through time, the mussels are very much still a major dominant part of the community. Later on, you started to see macrophytes coming in, and also other filter feeding invertebrates, tunicates and sponges as well. And this image is here just showing you what the mussels look like through the water. Not only are they filter feeders, but they themselves are habitat for a wide range of other organisms that live on and amongst their shells as well. So they're very much habitat formers as well. So this is where we sort of came in, following the restoration and following the work by Steve Hawkins and team in the 80s and 90s. A lot of the environmental parameters, so water quality, nutrients, temperature, salinity, various water metrics were measured by private consultancies for the years after the restoration and after the research stopped. And then we came along in 2012 and 2022, and we continued one of those metrics, and we were looking at Secchi depth, which is basically a measure of the clarity of the water and how deep light can actually penetrate through the water. So it's just one metric of many for water quality, which we have a long-term data set on. And as you can see here, you've got data showing you for the two different docks that we were really interested in, Queen's in pink and Albert in blue. And basically the story to take from this is early on, just after the restoration, both docks had very poor quality water and very poor clarity. Over time, Albert typically had greater water clarity than Queen's, but then in later years, in more recent times, since 2008, basically, both docks tended to have very good water clarity, which is one of the metrics indicative of good water quality. Some of you may know that in 2021 and 22, the Albert dock and the wider area actually received blue flags for their water quality, which of course is very relevant given the tourist status of this environment. So what about the mussels? So I said that they were initially trialed to be transplanted in, but we had this natural settlement in 1989. And this is showing you how they got on basically post 1989 here along the x-axis, all the way up to our sampling dates in 2012 and 2022 after Steve Hawkins and team stopped in the late 90s. And this is just basically showing you the density of mussels on the left axis and the mean length of mussels on the right axis. And as you can see, there's sort of a relationship between density and length. Over time, the average length of the mussels tended to go up. And over time, particularly in Albert Dock, there was a huge settlement of mussels early on with very high density, but very small mussels to begin with. But over time, the two docks converged in terms of density, and they pretty much stayed the same from the late 90s up until when we were sampling in the 2000s. In the samplings that we did, we found that the length of the two locations, okay, so this is Albert and Queen's here, had actually reduced significantly. So this could be partly due to a die-off of the adults, plus a major settlement event happening at that time, which of course reduced the average size of the mussels. I can say that in July 2022, there was a major salinity drop linked to the Leeds-Liverpool Canal bringing fresh water in, which led to a big salinity drop, which would have been significant for the mussels. Of course, we can't say for sure if that led to the die-off of some of the larger mussels, but it certainly could have played a part for sure. As I mentioned, mussels are filter feeders. And given the size and density of these mussels, they're really, really important in this environment. And they undoubtedly do contribute to the improvement of the water quality. We did quantify the sort of filtration effect of the mussels at different depths and in the various different docks. And they do certainly carry out that function. But importantly, in this environment, because it's closed off to the wider marine environment, we really do need a self-sustaining population to be able to continue to perform this important ecosystem service. And as I mentioned, the salinity drop in July 2022 is a bit of a reality check in terms of the importance of controlling and maintaining the salinity regime and the hydrological regime in maintaining these important mussels. So just to sort of introduce you to some of the other taxa that also have colonized the docks on the walls, but also importantly on the mussels themselves. This is just showing you the data from Albert Dock here. We have 1989 at the top panel, 1992, and then 2012 when we revisited the docks. And it's showing you various different groups along here at the different depths going from the surface down to 4 to 5 meters. And as you can see, in 1989, there wasn't a huge amount of diversity evident in the dock, but we did have predominantly mussels and some bryozoans and tunicates dominating that environment. A bit of green algae at the surface at that time. As we moved through time, up to 2012, when we went back and did full biodiversity surveys, you can see that there's quite a lot of darker green throughout the various different groups and also at all depths. And this is basically telling us that mussels weren't quite as dominant, but we did have many other groups now actually penetrating to all of the various different depths as well. And importantly, many of these groups are filter feeders. So even though the sort of density of mussels might have eased off a little bit, we have many other filter feeders that can compensate for that. So they're still very much carrying out that important function. So this conclusion to all of this really is that the mussels were a good example of nature-based solution. This image is just sort of showing you a summary of what I've just said. So domination of smaller barnacles and bryozoans to begin with. Mussels arrived in 1988, fortuitously, not planned. The mussels, of course, grew over time. They created habitat for many organisms, as well as providing a very important biofiltration function. And importantly, careful maintenance of the hydrological regime, particularly salinity, is important to maintain this self-sustaining population over time. So we have 40 years of data, but it'd be very good to continue to monitor this to see how they do over time. So just to put this in a wider context, this is an example of a nature-based solution, but I'm a marine ecologist who typically works on coastal infrastructure and marine artificial structures. And our particular field of nature-based solutions is greening of grey infrastructure, or GGI, or GBGI, depending on which term we want to use. And this is basically where we try to encourage biodiversity to be increased and enhanced on artificial structures, with the idea that that will improve the functioning and ecosystem service provision of coastal infrastructure. We produced a paper last year, which was a major paper to produce. There's 51 co-authors on this, and it was very much sort of an update on the state of the art of where the field is. So if you are curious about that, either you can go find it in maritime engineering, or please do send me an email. I'll gladly send it on to you. And just bring it back to Reclaim. So this is an example of one of the kinds of projects that I work on coastal infrastructure. This is living seawalls in Plymouth, and as you can see here, there are these many modular units here with different surface textures. This was installed in 2023 near the Mayflower Steps in Plymouth. As part of this, we are very grateful to support from the Reclaim Network, who kindly funded a workshop where we brought together some key stakeholders from the City of Plymouth to basically try to gauge their perceptions of greening of grey infrastructure or eco-engineering more generally, but specifically also their view on the living seawalls in Plymouth. And that's just an image from that workshop there to show you, just some of the activities that were going on. Brief update on that. Actually, I'm now in Cork in Ireland, and we're actually going to be installing a living seawall here in Cork, hopefully by the end of the year. So watch this space. This is part of a big global project, which is something that we're all very proud to be a part of. And I will just leave it there and say thank you to everyone for listening. Thank you to Amelia, Charlotte and Prashant for the opportunity to speak, and to Reclaim for supporting our workshop. And if anyone, of course, many collaborators, I'm representing many voices and research here. And if anyone has any questions, I'm happy to answer, and there are my contact details there.
Louise, thank you ever so much. That was fantastic. I've been to the Albert Docks September last year, and I was completely blown away. I went to the museum and went on the little tour, and it was, not only is it a really fun city, but the reclamation, I think, of those docks, it just was fantastic. I'm a deep lover of mussels as well, because I come from the east coast of Canada, where they boast the largest in Digby in the world. So maybe we should get together and do a sort of comparative study, and we can eat lots of seafood. So that's fantastic. Belen, I'm going to pass back to you for your next case study. Thank you very much indeed.
I did in the previous presentation, I tried to, thinking of the title of this discussion, role of water management in biodiversity, I tried to select some crucial points to trigger discussion. And probably the most obvious one in the relation of water management and biodiversity, from my point of view, would be maintaining the natural hydrological regimes. I mean, a very common, maybe one of the simplest ways of water management is let's save store water during wet periods so we can use them during dry periods. Actually, in Spain, which is round the corner, it's estimated that we would only have water in our taps at home 10% of the time if the water was not regulated, were no reservoirs. And this obviously brings a basic problem. I mean, if you collect water from the rivers and store it, you cannot leave the streams dry, because you would, I mean, kill the aquatic life. So one of the role of water management in biodiversity is making sure that we always allow this compensation. We call them compensation or environmental flows in the streams. But there are other more subtle impacts of this regulation of hydrological regimes. And I will bring up one of these effects that we were involved in a study, which is related to the changes in water temperature due to the regulation of water. This image shows it's a thermal image. It shows in color scale the water surface temperature in a river, in the main river that is flowing in this direction, and in a tributary. You can see this striking temperature contrast here. That's because we have a dam, a reservoir in the main river. The water is stored upstream of this dam and is released from the bottom, hydropower generation. And from the bottom, the water, particularly in the summer, comes up much colder. This has very important consequences on life in the river, because most of the, if not all of the aquatic organisms are cold-blooded, so they are very sensitive to the environmental temperature. So this brings another dimension of complexity into the management of water for biodiversity. I have another slide here about this. I'm showing now the same main river. The dam is here. This is the dam I was pointing at earlier on. This is a 100-kilometer long reservoir. And during the summer, stagnant water gets quite hot on the surface. This is the same of the reservoir where you can see the natural water, the running water arriving to the tail, and it's much colder. And funnily enough, here there has been a proliferation, a large increase in mussels as well. But in this case, mussels are the bad guys. They are an invasive species, and they have caused massive problems in water intakes. They grow around nets and infrastructure water. There have been other positive impacts. Now there are many catfish and quite a lot of tourists that go to the reservoir to fish. And this is just graph highlighting the impact on the water temperature of these reservoirs. The x-axis we have length along the axis of the river. And in this color, we can see temperature of the river running, and we can see this high increase in temperature when it plunges into the reservoir, into the stagnant water, and getting cold when it's released from the bottom. We could monitor these impacts throughout the year using satellite images again. And another, I think, very, very important intersection between water management and biodiversity is in wetlands. Wetlands are hotspots of biodiversity, and they've been really very badly hit in the past by humans. In the 19th century and even beginning of the 20th century, such a huge land of wetlands has been desiccated to use it for farming and food production. Now, at least in Europe, we are reversing a bit and trying to restore some of these wetlands, but they are still again in danger of climate change. And I have here an example of wetlands hit or affected by human water consumption, by the abstraction of water, groundwater. This is an area in Spain, a wetland area in Spain, that is fed by groundwater. This is mainly the discharge filling these wetlands basically from the groundwater. And around this area, there have been quite a lot of farming. This is a satellite image where we tend to represent very healthy green water, very healthy green vegetation in red color. So this image, the redder, the more healthy the vegetation is, and the more water content in the vegetation. And you can see many agriculture plots very green, and that is in the summer. This is because they are being irrigated. And this is a wetland site. Dark areas, very black areas, represent open water. This wetland was in recession, diminished by increasing irrigation around. Here you can see that the open water surface 10 years later is much reduced. And well, in this case, satellite images were used to spot illegal abstraction of water and to stop that, of course. And I will show you an image in 2010 where the amount of irrigation farms being irrigated during the summer has been dramatically reduced, and the extent of the water, the open water in the wetland, has increased. This is somehow a success story, at least for the biodiversity sustained by the wetland. Actually, we worked together with UNESCO to publish this management and protection of Mediterranean wetlands, groundwater related ones, that addresses these kind of issues. But what is, in my opinion, what is really key is that we can align, we can avoid the competition. If we have to decide between being fed or biodiversity, we will probably, go for growing food for ourselves. So ideally, to ensure, in my opinion, long-term sustainability of wetlands, is to find the aligning, I think it's written somewhere here. Yes. Aligning the livelihoods of humans with conservation goals. Maybe exploiting wetlands for tourism, or finding the way in which they help sustain population as well. We don't need to desiccate and use food. And here a few more examples again with the aim to trigger discussions. Well, these are another of a couple of challenges brought up by the stakeholders regarding water management, water and ecosystem degradation, and threats to biodiversity that we will be working with very soon. And this is another example of really fair competition for water in an area. This green line, this yellow line here represents the boundary of a catchment. This is located in South Peru. Black here we see the Pacific Ocean, and this area here are the Andean mountain range. There are some streams and rivers that they water snow melting from the Andean mountain range to the ocean, and they run through an area which is almost a desert. It's very, very arid area. And quite a lot of water is extracted for farming. You can see all these crops. Near here, very dry areas, and near the river, we can see this very green vegetation. And this comes from a little study we did to see how some of these wetlands and lakes were being depleted by the use of water by agriculture. And there is another very strong competitor for water here, which is mine uses. Not only use water, but also pollute it by. And all this is affecting not only these lakes and water bodies, but also very high, very particular and unique wetlands, which are called buffer islands. These green areas here are high elevation wetlands, which have been endangered as well. Here, these terrain elevation levels are only by mine users. And that's it. Again, I brought up a few things to encourage some discussion on this.
Helen, thank you ever so much indeed, and Louise as well. I think your use of these practical case studies and the snapshots, the photos, I think also helps. Sometimes they're satellite imaging, sometimes they're heat. I think gives us a really clear sense of the tremendous challenges. It brings it out of the abstract, I think, in many ways. So we've got a little bit of time. I think 15 minutes, is that right, Charlotte? So I might just check and see if I can, whether there are Q&A popping up. Let's take the one from Marvin, the first one, actually. It's a great place to start. I understand that we still need to be optimistic about saving our planet, so we'll give that as the context. But Louise and Bella, maybe I'll ask you both to come up with answers to Marvin's second question. Will those marine alterations specific to your case studies, which would become adaptive environment for marine species, still be considered natural marine ecosystems? So Louise, that's quite an interesting one, given the enormous construction and reconstruction of the docks. And obviously, we've seen a variety of marine alterations that you've been suggesting as well, Belen. So, Louise, why don't we come to you first for your suggestions and feedback there?
Sure, thank you. So I would consider them natural communities, as in they are natural communities, and in the case of the mussels and their communities, they naturally colonized. But would I call it a natural ecosystem? No, I would call it a novel ecosystem, and probably an artificial cultural ecosystem. I think cultural probably satisfies everybody. It's one that was shaped by both humans and nature, because clearly it is highly artificial. There's, it's concrete walls, blocks that built it, but you have natural communities living there. So no, I personally wouldn't call it a natural ecosystem, but a cultural ecosystem shaped by humans and nature.
Helen, your perspectives. You maybe want to come up here a little closer to the sound equipment. Thanks very much.
Your question is if we would consider it on camera.
Yes.
Yeah. Yes. a natural ecosystem. I'm a bit afraid of using these words of natural ecosystems because I know there are many nuances in them and I may not be very aware. My feeling is that they are not, but we have to rely on them because there are so many not natural ecosystems. All the agriculture nowadays, which takes up 1/3% of the land, sustains biodiversity. Is it natural? No, it wasn't before we were farming, but now it's there and we need it as well. So depend on what you, how the strict definition of natural is maybe. You know, in some areas, this country is a good example. Most of the country is farmed and still sustains the biodiversity. If now we remove all farms, we will be doing a harm to the carbon biodiversity, right?
Yeah. I was fascinated, and I'd love to get Louise's input in this, when you were putting up the picture of the dam. Now, perhaps this is a bit of a throwback, but I think traditionally, at least from what I've been taught, that, you know, dams are a necessity, but that they're an absolute blight, that they erase the biodiversity in the area. And yet you were suggesting that obviously they have their pros and cons. I hadn't realized the impact they have on the water temperature. There's an instant sort of cooling effect. So do we need to slightly rethink our attitude to dams from a biodiversity perspective, and specifically from what they do to, you know, to the water sort of aquaculture, I suppose?
Yes, it definitely needs attention and consideration and knowledge on how it works. Example, the point, I mean, basically the dams, one of the main thermal impacts of dams is that during the summer and hot months, the surface of the water is heated higher than the bottom. That causes, due to the top water is lighter, the density is reduced. This causes a thermal stratification, which makes the water body very stable. That it inhibits the vertical mixing of water, which leads to lack of oxygenation at the bottom. Okay. So this has tremendous implications in water quality. And what we need to be is aware that this is happening in order to minimize our impact. One of the things, for example, is the selection of water to at which height of the dam we select the water to discharge downstream or sustaining the environment. If you take water from the bottom, that will be anoxic water. That will cause problems. But you can take it higher up. There are towers. Though for hydropower generation, you want it from the bottom, which was higher.
Yeah.
But is first of all knowing the problem and then thinking of
an appropriate solution, obviously. Now, Louise, you weren't specifically talking about dams, but you were talking about locks and the change, and it's a magnificent set of before and after photos. Obviously, the sort of 1980s photo of Albert Docks just like silted up completely. And then obviously the removal of all the other, I mean, I think you mentioned locks, but what's the role of locks in the transformation of the docks?
Yeah, so there are many intakes from the River Mersey to various components of the docks, and then the docks themselves are all interconnected with interconnecting lock gates. So the whole thing is interconnected in some way. It depends on which direction you go in, of course. But yeah, the lock gates play a major role in the flow of water and the control of the flow of water. So I don't know what the management regime is like now, but certainly they used to open the docks, the locks every now and again to sort of allow, you know, replenishment of the water. And of course, that's quite important from the mussels perspective because it allows natural settlement to come in from the River Mersey. Otherwise, you're just requiring it to be, you know, the mussels themselves inside the docks to be doing that. One thing that I did experience from working in the docks, it was completely separate to this actual project. Prince's Dock, which is to the north of the dock network and the southern docks anyway. That's where the Leeds-Liverpool Canal comes in. So that dock is actually completely freshwater. But they had a weed problem in that dock where there was a a freshwater plant that was basically taking over the entire dock. But because it had a lock gate connecting it to a marine water dock, one of the solutions that we advocated that they might consider to try and get rid of the weed problem is to just temporarily flush that dock with the salt water to possibly just reduce it in the first instance, and then allow the fresh water to come back in. So in some ways, the actual intermixing of water can be used as a management technique as well. Of course, you would sort of not want to know exactly what you're doing, and there's pros and cons to all of these management techniques. You might be it might be a positive in one sense, but of course it has negatives in other sense, as do all of these nature-based solutions.
Louise, can I get you maybe to ask a question to Belen and vice versa? It's very nice to get sort of an interaction of our presenters. Is there anything that Belen presented, particularly on the South American aspect of your presentation? I thought was absolutely fascinating. Anything strike you as interesting there, Louise?
Well, I was actually curious about the mussels. I know, so I see mussels as a real positive, and I just think it's a really nice counterpoint to see that mussels were
That's
less
right. You did
desirable
say
in
they
your
were the bad
system.
guys. So
can I ask you about the mussels and how they're perceived?
So maybe we will have to take you there to help us follow the population of mussels. And I know they are an invasive species. They are called zebra mussels.
Yep.
You know them? Yes.
Mm-hmm.
Unfortunately, I don't know much details. I was in the hydrodynamics and observation of the water body more than on the mussels side of things. But they seem to be growing very quickly, displacing some other animals or in the reservoir, in the river. And one of the main problems from the water management, the dam managers, is that they tend to stick to nets and for intakes of water and block. So they have to conduct often maintenance operations to remove mussels. It's quite costly for them.
Yeah. Yeah. I'm aware of the freshwater mussel. I presume it's Dreissenia. Is the genus. But I used to work on a marine species of mussel. It was called Perna viridis, which was the green-lipped mussel, and it was the most beautiful green. It was actually the color of your jacket, Amelia. They were the most beautiful animals. But they were from the Pacific, and they caused problems in coastal marine settings. Where in Florida, where I was working. As a rocky shore ecologist, there are no rocky shores in Florida, so the only hard substrates I was able to play with were bridges and piers and hard artificial structures. But they were perfect habitat for these green mussels. And all around the Gulf Coast of Florida, you have a lot of power stations, and of course they have these inflow takes where they take the water in from the marine environment. But the green mussels were causing problems very similar to your ones, and where they were clogging up the intake pipes. So of course there's a lot of money that was spent every year to try and control this invasive mussel. But of course, native species can become invasive in their own environments. If the conditions are so. Yeah.
Thanks, Louise. Belen, question for Louise on any of her overviews?
Well, I was wondering if there is any, are they used for human consumption, these mussels, or not? Is there any plan? And I was thinking of the implications of water pollution, because they filter the water, but I believe they also may retain quite a lot of pollution. And I also thought for a moment of these areas in South Peru where there is quite a lot of mining pollution, and I know that food there is high levels of heavy metals, etc. So I was wondering, are they being used for human consumption, for example, or?
So currently, no. The mussels that are in the docks at the moment, they are not for human consumption, and I don't think anybody would recommend it. Initially, we're talking like the trials that I spoke about at the beginning. So before the natural settlement happened in 1989, and before the docks were used by ships, in modern times, the plan was that they were actually going to put a mussel aquaculture facility in the docks with the view that they might actually be used for human consumption. That failed, and then of course the natural settlement happened, so they didn't need to trial anymore or experiment with it. But of course, over time, the docks started to get used more by not commercial entities, but like private boats. And of course, with the connection to the canal, you also had boats going from the canal as well. So there are a lot of pollutants that end up in the docks. Of course, the mussels take care of a lot of that, but you would definitely wouldn't want to be eating them. The additional problem that you have with the docks, which is it's quite a unique ecosystem. There's nothing really that occurs like this in nature, where you don't have a tidal regime in a closed body of water, is because it's so closed. Of course, any pollutants really stay in situ, and there isn't much flushing to actually clean it out, if you will. So no, definitely wouldn't recommend eating any of the mussels from the
There are
dock.
better things to eat in Liverpool, right? Excellent. I'm going to continue to invest in Herna Verida jackets. So thank you for that, Louise. Thank you both very, very much. This is excellent panel full of lots of fantastic, really lively examples, really memorable ones as well. So we're going to move on to our final case study now, and I'm going to give over to our chair, Thomas, who's going to introduce himself and present his case study. Obviously, Thomas coming to us again from the Reclaim Network, and then sort of call and response, if you like, between him and Prashant. So over to you, Thomas. Thank you for joining us.
Yeah, thank you very much. Thank you for the introduction and the opportunity. Yeah, so my name is Thomas Kielsen. I'm a reader in water engineering at the University of Bath and been part of the Reclaim Network and work closely with Professor Kumar on this. And I'd like to extend a thanks to him for inviting me. So in the network, I guess I represent the more engineering bit of the network. And as such, our case study is probably less to do with biodiversity than what we have just seen. But nonetheless, I think it is linked. So I'm just going to have to figure out how to share my screen. I hope that works.
There we go.
Yeah, we can.
Right.
Perfect.
So,
Thank you.
thank you. So, as part of the Reclaim Network, we received a pot of funding to do an interdisciplinary multi-institutional project on catchment scale benefits and disbenefit of green and grey infrastructure. There's emphasis on urban rivers. And it involved quite a lot of partners. It involved ourselves. So we are the Department of Civil Engineering, the University of Bath. It involved Professor Kumar's group at University of Surrey, the hydrological modelers from the UK Centre for Ecology and Hydrology. And the study itself took place in the city of Cardiff, and we had people from the city of Cardiff, in particular the flood management team in Cardiff were very heavily involved in this as well. So this is the case study we're looking at. We're looking at the city of Cardiff. Particularly, we're focusing on this blue box in here. So the red polylines you're seeing on this map are catchment areas, and I'll get back to them shortly. They are catchment areas that drain into urban rivers that are causing all sorts of issues in Cardiff with respect to local flooding. At the same time, Cardiff is, like any other city, is expanding, and they want to expand the city. They're trying to protect the green belt, which means they have to densify the city itself, which comes at the expense of some of the green areas. So one part of the project was to assess what's the what's the impact of removing or having green space inside the city with regards to local scale flooding issues. The other part of the problem that this benefit is if you were to increase the green space, like trees and vegetation and such, you're likely to create wooden debris as a result. And as it happens, this is a big problem for local authorities up and down the country, that wooden debris eventually end up in our rivers, and it clogs the rivers and it blocks entrances to culverts, etc., which requires cleaning, which is expensive and also a health and safety issue. So we were trying to look at these two aspects of green infrastructure. So step one in our project was to try to map out the actual land use within Cardiff and identify, with the help of Cardiff Council, areas of potential future development in here. And you can't really see, this is a big area of Cardiff. Got the city itself in the sort of center of the green and the bay out here. And inside the city, we've identified, Cardiff identified potential and already agreed upon sites where new housing is going to go up, and therefore putting down urban infrastructure such as roads and houses and removing the green infrastructure as a result. Now, these were some general land use images, and it took quite a lot of work from our colleagues at Surrey and CH to make this into a useful map for detailed hydrological modeling of flood responses. Once we'd done that, colleagues at UKCH used their new hydrological assessment tool. So this is a tool they've developed that are specifically trying to answer or to represent the impact of nature-based solutions on flood flow inside cities. So it takes things like land use and ponds and rainfall characteristics and such into account. And they did model, and they modeled various development scenarios. So what you see on the left is the land use scenario, and what you see on the right is the potential impact of removing green space and replacing it with new housing development. As you can see, the changes in flood flow that results from development are sort of indicated in blue. Everything in gray didn't really get impacted, but the blue areas is where the developments go, and there you can see a very distinct increase in flood risk, measured in you know tens of percentages, so up to 50 or 60% in some cases, but the impacts are rather localized. But it does suggest that you have to be very careful if you remove green infrastructure, and it is likely to have a very localized impact. Now, the other problem we looked at, and we are engineers, so we're very interested in sort of managing these problems, was the effect of green infrastructure on debris. So a lot of places in these urban rivers in Cardiff are draining green areas, both within the city and upstream, lots of gardens, lots of parks, lots of upstream green fields. And what happens is that debris ends up in the river, wooden debris in particular. And we've got lots of these infrastructures you see here, which is a trash screen. So this is here to protect a pipe, a culvert that maybe goes under the city or goes under a road. And you don't want that to block inside, because then you have to get people inside this little pipe, all in there and clean it out, which is very dangerous and expensive work. So that's why water managers up and down the country put these trash screens on. But they, of course, as you can see on the right, get blocked, and you need to dispatch a team to clean it up. And if you don't clean it up in time, you've created effectively a dam, a reservoir across your river, and you're going to flood the adjacent area. So what we were trying to do here was to say, okay, well, we got this, these images are taken by CCTV cameras. So they're monitoring with CCTV. Could we develop a machine learning model that could look at these different images and tell us, detect automatically whether we see a block on this image or not, so that people wouldn't have to sit and look at the cameras, but be alerted automatically. So we looked at a particular trash screen here in the north of Cardiff. It drains a green area here, so it's a foresty area, but there's also quite a lot of suburban development here, and people do gardening, and they tend to throw their garden waste, tip it into the nearby river, which end up clogging this trash screen a bit further down here. So the council had operated a CCTV camera looking at this trash screen for 3 years, taking pictures every day. And we got permission to scrape all these images off their system. And then we had some students helping us labeling them. So they looked at each image and said, do I see a block on this image or do I not see a block? So they labeled every image we had scraped off, and we double checked with the flood managers whether they would consider this blocked or not. Some of the images were poor quality, I'll show you in a second. But we ended up with something like 600 images. The majority of them did show blocking, but some showed no blocking at all. So problems can arise when you do this sort of thing. Sometimes camera lose connection, you get just noise. Sometimes things like vegetation growth in summer happen. So a branch decides to grow in front of the camera, and to our dumb machine learning algorithm, that looks like a block, but it isn't. It's just a branch that has to be removed. Sometimes there was splashing and rain on the camera. In other cases, so this is a different from a case in London we've investigated. A spider, for instance, decided to build a net across the camera, so you capture a spider instead. Of course, that's not a blocked trash screen, but it would look like that to our algorithm. So we had to filter all the images as such. Once we've done that, we try to define a new machine learning model, and we use something called logistic regression modeling, which is essentially an extension of normal linear regression, where you have one variable. So on the left, where you have one variable x, you have some values of x, and you try to predict some value of y. You do that by collecting data and drawing some lines through it. In logistic regression, you have the same problem, just that you have only two categories. You have images down at the bottom which are labeled not blocked, and images up here that are labeled blocked, and then x here represents some feature of the image you're giving it. So if the images has features that are on this side of the graph, there's a high chance of detecting a block. Whereas if you're down here, features of the image are down here, then there's a low chance of detecting a block. So we fitted this kind of regression model. So we took the images. The images are input into our model. That is this red line. And we can feed all sorts of images through our model. And just go back here. So if the features of our model are up here, if a new image come in and it's got a feature that's has a high value of x, we're very likely to get a blocked image, and we would issue a blocking alert. Because we had an imbalanced data set, so we have more blocked than unblocked images, we created different versions of the data set where we try to make as many blocked as unblocked images by augmenting some of the images. This was a process of trying to create similar images from the images we already have. I don't want to go too much into detail, but what the case study shows is that if we create an what we call an augmented data set, that means we have just as many blocked as unblocked images. And we trained our machine learning model and then fed it some images of trash screens, blocked and unblocked, that it had never seen before. We could measure the performance of our model, and we do that by using terms like accuracy, recall, and precision. So they're all measures that try to measure how well are you predicting, how well is our machine learning model predicting things it hadn't seen before. So if we feed it a picture of a trash screen that is blocked, what's the chance of how many what's the percentage of time it would predict this correct, which is accuracy, and turns out that it's about 88% of the time. So I'd say almost 90% of the images, our machine learning model will give us a correct prediction of the status of the trash screen. So we thought this was quite successful. So to summarize it, I think we were funded by Reclaim to undertake this project, and I think what we have shown is quite a successful case study. The NR model, so this is what colleagues at UKCH did, it developed this model and applied it, and it turns out this is quite an easy model to use, and based on the success from this case study, they now have an ambition to build this into their more integrated system of nature-based solutions. So considering not just flooding, but other aspects such as biodiversity and other ecosystem services. So this was a case study for this. So I think there's some innovation coming out with regard to this. In Bath itself, we've continued working on the idea of these trash screens and the monitoring and the alert system, and we're now in the process of implementing our machine learning models together with the council in Cardiff into an actual app, so that as you can see on the right, they have these cameras looking at the trash screens, and what we want them to do is to take the images automatically, feed them through our machine learning model, and then issue alerts to them on their, in some form or another, to a website or their iPhones or whatever, so that they don't have to sit and monitor their trash screens anymore. They can just they'll get alerted when there's something they have to worry about. So hopefully that'll save them time and also be more efficient and use their scarce human resources more effectively. On a wider sort of scale, I think this has shown that this idea of using cameras and image analysis, which was new to me when we started, I think is quite exciting and has lots of promising application, given that cameras are quite low cost and very inobtrusive instruments to put out. So I think there's lots of scope for innovation, not just in flood management here, but across sort of environmental management in cities, especially in these sort of urban environments where it's often difficult to put out expensive and fragile instruments. So I'll stop here and yeah, happy to discuss or take any questions. Thank you.
Yeah, thank you very much, Thomas. Yeah, is anybody having any questions for Thomas? I think we got a few minutes actually in this session. Maybe I could possibly bring in some of the information from the Reclaim side on how the Reclaim is possibly helping with developing the case studies in terms of the flood mitigation. Is that all right, Amelia?
Yes, absolutely, Prashant. It's an opportunity for you, effectively as chair, to talk a little bit to Thomas about the nature of the case study, but also how it reflects more broadly some of the objectives of Reclaim as a whole. Just with SDG 6 a little bit in the background there as our main calling card today.
Yeah, so I think we could do it in two ways. We got around 15 minutes actually in this session, if I'm not mistaken. The one of them is if the colleagues on the call, if they have any questions, and again they can ask, or even is a comment actually, just leave them there so we can raise it with Thomas, and I will be happy to answer them as well if they are relevant to me. And the other thing is obviously reflecting on on these case studies, but also how, let's say, some of the activities through Reclaim and the other surrounding projects colleagues have been involving, helping with the flood mitigation.
Prashant, there's a question from Marvin, if you want to answer that now. Or Thomas, or do you want to?
Oh, yes. So there is a question from Marvin, actually. Possibly, it says, should we already accept that we would be living a flop-induced environment and adapt our habitations around it? I did not fully understand it, but Thomas, do you have any thoughts about it? Should we already accept that we would be living a flood-induced environment?
I'm guessing it should say flood.
Maybe flood, yes. I think it's.
But that's just my guess. Otherwise, otherwise I don't have an.
Yeah.
Well, so for sure we should. I mean, that's. I think floods are it's just as droughts are a natural occurring phenomena, and one that's very difficult to engineer your way out. I mean, you could, and we talked about reservoirs just before, which is a rather perhaps a bit of a brute force way of mitigating floods, and probably too expensive, and the consequences are too wide. So I think there is a need to develop these sorts of smarter solutions that are less intrusive, perhaps requires less traditional. I mean, traditionally we would have constructed our way out of it. Just pour more concrete, pour higher defenses, more ponds, more upstream storage ponds, etc., without really considering any much of the secondary impacts of this. Because if you take a purely economic cost benefit approach to flood defense, I mean, you're defending city centers, basically, like Cardiff, and that's expensive. If that floods, that's very expensive. And so it trumps most things. You can do almost anything as long as you're willing to protect that. You can justify almost anything, but it might not be particularly sensitive to the sort of surrounding ecosystems and such. So I think there is a need, and there should be a drive to smarter ways of doing things. And I'm not saying this is the way of doing it, but this is certainly something that tries to harvest new technology, cheap technology, and new capabilities, as an example. So
no.
I think that's
So I believe that I mean, just to reflect actually on this point, I mean, you have basically the two ways. Definitely, you could see the impact of the climate change. So one of the ways is the control at the source itself, right? So how the flood itself could be reduced, or at the first place. And the second thing is then it comes the mitigation aspect of it. I mean, how do you, when things happen, then how you mitigate them? So if you wanted to think about how we control at the source itself, so a lot of it is happening for two reasons. The one is the climate change impact. So you got a very changed sort of, the pattern of the rainfall, and then you are seeing the water, pouring in just in burst actually, and the drainage system doesn't cope, and this is why the flooding happens, right? So that's one aspect of it. So basically, anything we are doing to contribute to alleviate or mitigate the impact of the climate change is going to help actually with the flooding as well, right? So that's one aspect. The second aspect is, and then related to it is the cities actually, or the urban areas we are designing, but they were designed to consider the past sort of, the history, and taking in consideration some sort of development. But then, the things which are happening is quite, they're not really, planned actually, and they're happening. The second aspect is the mitigation aspect. Then when things happen, what do you do? So one of the areas which a lot of colleagues actually on this call has been working is, can we use the nature to fight against the natural hazards like the flooding? And this is where the nature-based solutions, or the greening and the green blue infrastructure interventions comes in place. So for example, for the urban areas, There are a lot of issues in terms of bringing in the greening, and that greening could not only help with the flooding, but can also bring quite a lot of the benefits. Now, how does this help actually? So one of the ways of it helps is if, let's say, you have got the vertical gardens, you got the green walls, or you are putting actually the greening around the streets. So it basically delays the flow, right? So what happens is if you have the paved road or the paved, the surface, any water comes in, it will just run very quickly to the drainage system, and then it will fill up very quickly. But then what it does is it basically slows down the flow, and that slowing down helps actually in terms of the mitigation there. So you could see some of the case studies which Daniel was presenting, and as part of the reclaim, there has been quite a few case studies we funded, which looked at this aspect, but also looked at the co-benefits of it. So, for example, it helps with the flooding, but what does this help, or what does this mean actually in the context of the air pollution, overheating, biodiversity, health, and well-being? So I think it's a good body of work which is emerging in this particular area. And whenever we are making those decisions, I think we possibly need to think more holistically so that we are not just focused around one aspect. Rather, we could see actually what are the other benefits and how we can possibly help our the urban environments to cope with this flooding and other environmental challenges. I can see also there is another question from Liliana Pimentel. Thank you for the presentation. Have you seen any changes on policies and regulations after the implementation of the trust monitoring? So I think it's for you, Thomas.
Yes, thank you for that. Not yet. No. We're still piloting, but I think there is a general push to ask local councils to implement more cameras to support them in monitoring, to try to be more effective in managing this debris collection. So cameras are going up, I believe, but I still think they're not necessarily equipped with this capability. So they're still requiring manual intervention. They're still requiring somebody to sit and look at it and decide whether they're blocked or not, which might or might not be very helpful if they, for instance, block at a time when everybody has gone home. Somebody has to actually sit and look at it. So I don't think it has. Nothing has changed yet, but hopefully these capabilities could be a push to help mitigating flood risk in urban areas through smarter technology.
Yeah, perfect. So, and there is also another question from Marvin Tejeda. There is a declaration from a marine scientist that roads and habitations should be constructed 7 meters above the current natural ground line. What do you think about it?
Sorry, that.
So there is a declaration from a marine scientist that roads and habitations should be constructed 7 meters above the current natural ground line. What do you think about it? So my understanding of this question is that when you're building the roads, actually it has to be 7 meters above the natural ground line, just to make sure that during the flooding, possibly
during flood, yeah,
it's safe. So I think the question really is, what's your thought about it?
Seems sensible enough. If I think it depends. I mean, I think it's difficult to give a hard number like 7 meters or 6-7 meters or so. I think it depends on the circumstances. If it's not a very important road, you might not care very much if it gets inundated every now and then. Are you prepared to accept it? If it's a critical bit of infrastructure that needs to be functioning at all times, then you want to spend quite a lot to prevent flooding from happening. And if that involves moving it 7 meters up, then so be it, or building a big wall. But again, I think it's a trade-off between what you're prepared to accept and the risk you're prepared to accept versus the consequences you're prepared to accept.
Right. So I think there is I think there's just more like a comment actually, which is I agree about the mitigations, but the rate of rain is high, that it comes beyond the range of saturation. Yeah, that's what we were sort of talking about, the flooding. So the flooding is usually when you got, the big burst of the rain,
Yeah.
and the system cannot cope with it.
I mean, I think that is a good point, and I think, Prasad, you were alluding to it before, that you try to do something upstream. You try nature-based solutions. You try to build sort of leaky dams, or put things in the way that keeps water back, maybe made of wood and so. But those sort of interventions are obviously helpful. They're very helpful for smaller, for flood events of a relatively small magnitude. And they obviously have lots of auxiliary benefits for biodiversity and carbon sequestration. So, but when for flood defense, what we're really talking about is events that would happen once in a century. Typically, those are really big events, and at that point, lots of this debris you've put in place will not stand. It'll simply be washed away. And not only do you have to deal with the water, now you also have to deal with the debris you put in to try to prevent the water in the first place, because it's now been dislodged and is coming towards you as well. So I think there is a need to ensure that these interventions that are put in with the best of intentions are actually robust under these most extreme conditions that most people probably wouldn't, you might not experience it in your lifetime. I mean, that's the sort of size of magnitude, the magnitude of these type of events we're talking about. So there could be lots of unintended consequences of this that could cause real damage downstream. So I think we obviously, and I think Reclaim Network has done a lot of work here. We're actually only in the early phases of understanding how well these systems perform and how robust they will be, and under what conditions, certainly when it comes to flooding, they will be effective as such. So I think there's much more work to be done in this area.
Perfect. Yeah, thank you.
I'm just going to jump in now and thank you very, very much, and Thomas, for a really interesting panel. Once again, I mean, with not just the clarity that comes with a case study, but the visual cues and clues that Thomas provided, as well as, thank you, a really nice context as to how you got into the issue in the first place. And Prashant, thank you for giving us the background of Reclaim as a whole. It's clear that there's been some very sensible allocation of funding. And I think that's really important, because as CFAL Surrey itself begins to grow, and certainly we're looking for ways in which to support the research intensity that grows out of Reclaim and the Institute. We want to be able to make those same choices, sensible direction of research to be able to solve real world problems. In this case, it's the intersection of water, agriculture, and biodiversity, but you can certainly see how that is going to be spread across the SDGs as a whole. So thank you very much, both of you. I'm going to turn now, in our last 15 minutes, to the lovely Dr. Ebru Kanan-Sokulu, who is graciously joining us online from Geneva. I had the privilege to meet Ebru when she came here to the University of Surrey to help launch CFAL Surrey in November. It seems both just yesterday and also quite a long time ago as well. So we're delighted, because she's been an absolute champion of CFALs in general, and the CFAL Global Network, which Surrey is one of. These are our sister centres, and we've also already, I think, made inroads in connecting with them and finding those interconnections. So Ebru, over to you, because I know that hopefully you've been enjoying today, and you've learned, as I know I have, lots and lots about SDG 6 and its accompanying challenges. So over to you for a few words. Thank you.
Thank you very much. Thank you very much, Amelia. It's a great pleasure actually to join most of the webinar, which has been tremendously, a breakthrough, I think, as it covered very technical aspects of water management, biodiversity, agriculture, but also I'm very glad that, and I thank you for this, for bringing us as UNITAR with all these fantastic colleagues who are working in different aspects of water issues, ranging from, very technical to social scientific issues. So indeed, it has been a great journey for me. I started the webinar in Warsaw, then I joined also in Geneva. So I greet you, everybody, in this closing remarks from Geneva, from UNITAR. And I want to thank all of you to start with. So as UNITAR, we have been working within the UN water system since the last couple of years as one of the founding members within the UN system. And so it is an ambition, and of course it's a great responsibility to cover with many challenging, pressing issues that relates to water. As SDG 6 has been, among all these SDGs, has been slightly undercovered, has attracted very little attention, even though the theme is extremely vital to everybody in different parts of the world. We know that the academic community has advanced tremendously, of course, in terms of scientific findings and dissemination of the empirical research. So, and we're very glad that as the United Nations agencies, we are very glad that we are collaborating with the academic institutions. And that's why I greet all the colleagues from different universities who work in this particular field, and welcome to the family. So, dear Amelia, thank you very much. It's been really very rich, this first kickoff webinar, series that we have the privilege of starting with you, with SIFA Surrey, with Reclaim, and the University of Surrey. And so we are very grateful for this, of course, for several reasons. First of all, when we started the streams of change as an idea, we were thinking about, okay, water is something quite unique, and among all the 17 SDGs, it's a very technical issue. There are different SDGs that cover also to different degrees the issues related to water management, water scarcity, water under, life underwater, and so forth and so on. So, but of course, the more that we delve into different aspects of this great theme, we explore that there is actually a lot to cover. So this Streams of Change webinar series aims this, right? So it has been fantastic to start with this month with you, with all of you, because the idea is, of course, to locate water in a greater spectrum, which shows everybody, all the audience, all the participants from different disciplines, from different institutions, that water is located actually in all aspects of life. So this month we are covering biodiversity, agriculture, but next month we're going to be covering another aspect of water, as the UN, as we know, that has important days of the year, and we want to locate water in those important days to create the awareness, of course, and to bring all the expertise accumulated in different aspects. So we'll continue with water with indigenous people, water with youth engagement, water with, clean water and sanitation in education, and so it goes on and on. So this is a great start, as I said, that we were very lucky to start with you this webinar series to create the awareness and to create a network of community. And so, well, of course, SIFA Surrey, it's been my privilege that I was at this beautiful university when we launched, and it's very impressive. It's very impressive how SIFA Surrey hosts a great, variety of colleagues who are working, and not of course only in water, but in a very wide spectrum of different themes and branches of sciences. And of course, it's very well, very supportive of CIFA Surrey. CIFA Surrey is one of our CIFA training centers across the world, in the CIFA Global Network, which of course locates the water issue in together with some of those training centers, and so we really rely on this expertise. So thanks also for that, dear Amelia. So what are the key lessons that we learned? So just to wrap up today in this 3-hour journey with the fantastic colleagues and experts. Well, I'll just try to be very brief because I know that my list is very long, but I think we can start with, like, some of the key highlights of our webinar today. One to start with is that water is about human rights, right? And we have to highlight the cultural importance of water. And of course, we have to highlight the financial challenges related to water management, and resilience issues, and so infrastructure, and so forth and so on. What I learned very interestingly is that the global water scarcity, noting that per capita renewable water is a simple but telling indicator. So I want to thank to Jonathan for this striking lesson that we can actually keep in our minds, besides several other statistics that needs to be really highlighted during this journey, right? So for instance, what is extremely important is the great divide between the different countries in different parts of the world with different levels of socioeconomic development, right? So from lower middle income countries to higher income countries. So this is a great variety in terms of access to water, and in terms of alternative mechanisms to generate drinkable water, for instance. So it all depends on the resources. So it's something that we have to keep in our mind, that to meet the domestic needs of our daily lives, we really need to generate alternative resources. So this is, of course, a big question related to economic development and the transfer of resources from certain parts of the world to the other parts of the world. So well, of course, needless to mention Sub-Saharan Africa, Oceania. So in terms of all these biodiversity loss, we learned also tremendously a lot. So which brings us to the health and sanitation issues, because waterborne diseases, these are all like in a big nexus that we have to remember. And of course, well, Reclaim case study is something that I really learned personally a lot. There is, I'm sure that there is a lot more striking data that will probably contribute to the academic dissemination of the issues. So we're looking forward to hearing and learning more about the case study and Reclaim's work. So we're very grateful actually that Reclaim was together with us. So what are the next steps? Well, of course, learning is an endless journey. So as I mentioned earlier, we will continue talking about water issues in every month on the monthly basis. And so these will be you know, shared with all of you. And of course, we are very much looking forward to contributing, co-hosting to each other and with each other many other events and training programs in the field of water. So, so thank you very much for joining this journey with us. And well, again, dear Amelia, I particularly want to thank you for your effort and for introducing us and the participants to this webinar to brilliant, you know, minds in academia in that part of the world. So thank you very much once again, and for everybody who joins us, and of course who shared the experiences and expertise with us and with our participants today. Back to you, Amelia.
Ebru, thank you very much indeed. I like to think of the experts surround me as inspiring minds. They inspire and they are themselves inspiring. Streams of Change is a fantastic output in every sense. It helps to, I think you put this very nicely, you know, it's disaggregating the complexity of something that looks very, very simple to begin with, but actually is perhaps received much less attention. And by really challenging and tackling it month on month, and we're delighted to be able to have done it this month and look forward to supporting future opportunities. We're really glad to have brought the expertise here at the university, the Institute for Sustainability and Reclaim as well. So my thanks to everybody who's jumped in and supported this panel. It's been a fascinating half-day session. We're delighted to support UNITAR in this, and I think we have a lot to contribute in terms of the content construction of the training from UNITAR, but also from what we're able to build here at CFAL Surrey. So my thanks to everybody. My thanks to you as well, Ebru. Prashant, thank you on behalf of Reclaim, and have a good day, everyone. Use water safely.
Thank you very much. Thank you.
Bye.
Bye-bye.
Thank you all. Thanks.